Welcome to this first class where we will learn how to successfully complete the course. During this first class, we will see a brief introduction to the Udemy platform. If you have previously taken courses on Udemy and are familiar with the platform, you can skip this section. We will then talk about the tools we offer and how to run a successful course. We'll move on to where we can get access to the training material and certificate. Then we will learn about best practices and learning tips. We will also talk about the system to ask your questions and get your doubts solved. And finally, we will talk about where we can get discounts on all our sites. We'll start now by talking briefly about the Udemy platform. We'll see how to set it up and how to use it. This is the Udemy platform, and we've taken a random course as an example. At the top, we have the title of the course, and on the left, we have the option to access the general platform. Then on the right side, we have the course content where we will see all the modules and classes of which this course is composed. We can go from one class to another by simply clicking on each of the classes, and the class will be played on the central screen. To know how to do a course successfully, we will see how to do a course successfully. To know if we have completed a class, we will see this icon in black in the classes that we have completed and this empty icon in the classes that we have not yet completed. Then at the bottom, we have a panel. We have the overview panel, which shows us a general description of the course and also our information, including the link to our LinkedIn account. Then we have the questions and answers panel. This Q&A panel is where we can find different questions about the course with the solutions and the answers to these questions. It can be very useful for us because someone else may have come up with the same question that we have, and here we can find a solution. Then we have a notes section where you can see some of our notes about each of the modules. The announcements where we will publish different notifications of the courses, and the ratings where we can see the overall rating of this course. Finally, the Learning Tools section where we can use these tools to manage events in the calendar and track the learning, or also to get PRS notifications. Finally, we can configure the execution of the different classes in a panel that appears when we get on the video. This one would be to pause and play. This other to rewind 5 seconds back. Then the configuration of the speed of reproduction and the time of reproduction. This is for rewinding 5 seconds back. Then we have the configuration of the speed of reproduction, which is very useful to adjust the speed of the video to the speed that we want that better adapts to us to our necessities. Then we have the option to fast forward 5 seconds, the moment in which this video is stopped. We can add notes here and also mute the lessons. We can activate or deactivate the transcription and add or remove subtitles. Then in settings, we can modify the quality of the videos and mention that our videos have been recorded at the maximum quality allowed by the platform, which would be 1080p. However, depending on your internet connection, you may see 720p instead of 1080p. You can leave it on automatically. In this case, what it will do is detect the internet speed, and based on that speed it will vary the resolution in which it shows you, or you can directly select the 1080p option and it will force all the videos to be seen in 1080p. But on the other hand, if you do not have a good internet connection, it may take you a little while to order the videos. And then here we have more options. Finally, we can activate the full screen, which would be this one here, to be able to see the classes better. Now that we have talked about the Udemy platform, we will talk about the general features of the course. As for the general features of our courses are concise. This means that we try to compress as much information as possible in as little time as possible. Therefore, you will find courses that have a lot of information, very compressed, but that requires little time to complete. This way you can learn as quickly as possible about a subject and quickly put into practice what you are learning without having to spend hours and hours on the theoretical part of a subject. Another characteristic of our courses is that we have a gradual increase in the level. You will find courses in which the first modules are more theoretical and the most basic concepts and fundamentals. If you already have knowledge of that subject, you can skip those first modules that are more introductory to advance to the following modules that will be more advanced. We do this gradual increase of the level because there are many students who do not have any knowledge about the subject, and this type of module is very good for them. If in your case you already have previous knowledge, do not have a problem skipping some of the courses. You can mark them as completed in order to obtain the certification as well. In addition, in our courses we go from theory to practice, that is, we do not skip anything. In the first modules, we take a more theoretical approach, and in the following modules, we move on to practice with practical codes and applied projects. Therefore, you will notice that the first modules tend to be more theoretical and the following modules tend to be more practical with applied projects and also usually more advanced. Finally, our courses are updated regularly, so please check the courses because every so often we add new courses, new classes, or new additional material. We have seen complaints about the accent or because the audio is not understood. To avoid this type of problem and make the audio more understandable, we have edited the audio. It may be more monotonous than the original audio, but this way you will be able to understand it perfectly and focus on learning the course contents. We also ask that you do not rush through the course evaluation. There are many of you who pass to evaluate the course in the first modules. Remember that these first modules are usually lower level and merely introductory, so we would ask you to wait until the end of this course to get a full picture of what the course is really like and the quality of the course. And once you have completed it, please leave us feedback about our courses. As for the material and the certificate, we will now explain to you how to get them. The material can be found in the first course modules, in the class called Course Material. Here you can find all the material of this course attached. In this case, for example, we can download the PDF presentation and also all the codes and exercises of the course. They are zip files, compressed files that you can unzip with any tool. As for the certificate of completion of the course, you can get it once you have completed the course in its entirety. For this, you will have to see that all the modules have completed 100% of the courses and classes. You will see this in that it tells you how many classes you have completed versus the total. Here, for example, it tells us that we have 5 of the 5 classes completed, and in this case, only 1 of the 3 classes completed. If for whatever reason you have already seen a class and you do not want to see it again, you can mark it as completed by clicking on the square. This way this class will appear as completed and will not be counted. If you have reached the end of your course and it does not let you get the certificate, it may be that you have skipped a class. Review each of the modules and you will be able to see the class that you have not completed yet. You can check it off so that it is complete, and then you can come to your progress and download the certificate. Now that we've talked more about how to get course material and download the certificate, we'll talk about how to get the most out of the course. To do this, we will explain the best practices you can use to study and learn from this course and share some learning tips. The first is to take notes and review. Active learning is proven to retain much more information than passive learning. Therefore, do not limit yourself to listening to the lectures, but we recommend that you take notes, generate notes, and then also generate summaries of each of these classes. You can use the PDF slides that are in the attached material to add your notes to the presentation. And finally, we recommend that you review it. If you study every week, for example, we recommend that before starting a new class you review what you learned in previous classes. Another recommendation is to adapt the speed of the course. Adapt the speed of the classes according to your needs. If you see that 1x is slow for you, you can set it to 1.25 or 1.5x, which is the speed we recommend, so that the learning is more agile and in less time you can complete the course, or at least the theoretical classes, and then focus on the practical exercises. If there is any section that you have not understood well or any class that after finishing you still have doubts about, you can stop the video and you can watch it again or go back. Another recommendation is to learn by doing. We recommend that you not only watch the theoretical classes passively but also try to develop all the exercises, try to replicate what we do, replicate the code, make small changes to the code on the original project and try to do the same, for example, changing the dataset. This will allow you to put into practice what you are learning and thus learn by doing. Then, as for the exercises, we recommend that you try to solve the exercises on your own and only resort to the solution once you have finished the exercise or in case you get stuck while solving the exercise. We also recommend that you do personal challenges, that is, that you try to apply everything you have learned in a practical project. It can be the practical project of your choice with the example that is most interesting to you or the data set of your choice. Then, as you complete these practical projects, you can use them as evidence of your learning and knowledge, along with the certificate of completion of this course. This will give you many opportunities in the workplace to demonstrate your knowledge and skills. Finally, we recommend that you expand your knowledge by using our course as a basis and also the additional material we offer you at the end of the course. You will also be able to search for additional information if there is a section or a topic that you would like to go deeper into or learn more about. Now we will talk about the process of resolving doubts. As you may have guessed, we are thousands of students all over the world. Because of this, we receive hundreds and hundreds of messages and questions every day, so we cannot resolve questions in the time we would like to. Instead of throwing doubts and waiting for the solution, we recommend a more successful pedagogy that will allow you to get answers in the shortest possible time. And it is the following. Keep in mind that most of the doubts you have had can be solved with the classes. So, if when you have completed a class you still have questions, we recommend that you rewatch that class. You can always stop and go back and watch it 2 or 3 times until you can understand the concepts and solve those general or basic doubts you have about the course. If you do not find a solution, we recommend that you access the questions and answers section of the course, which is the section here that we mentioned. In this section, you can find questions from other students who, like you, have had some doubts and have already asked their questions. Then you can also see the answers from other students and the solutions we have provided. It is very likely that your question is already in that forum with the solution, so you could get the solution very quickly. We also recommend that you search the forums. We can only resolve problems or error messages if we see the error code. Therefore, it is faster to look for the error message, copy it, usually the last lines of the code that returns the error message, and go to specialized forums such as Stack Overflow. In Stack Overflow you will find a lot of people giving support to questions and doubts about data. So, just search or copy the error code, the last part we mentioned, and search for it together with the word Stack Overflow. We are sure you will find your same question with possible solutions. Finally, if with the above options you still haven't got the solution to your questions, feel free to write us a question to Udemy Q&A and our team will give you support on some topics they can. Please note that when you have questions related to code errors, you need to provide us with a screenshot of the error so we can see what is going wrong, otherwise we won't be able to help you. So try to document as much as possible the error code or your questions so that we can help you. Finally, let's talk about discounts on our courses. There are 2 ways in which you can get discounts on our courses. One is through the Udemy platform. Udemy periodically offers discounts on all courses, therefore, you could get our courses at a reduced price. And if not, another alternative is to resort to our courses. We, from time to time, post discounts on our LinkedIn network. These discounts are maximum, that is, you will be able to get our courses at the minimum price that the Udemy platform allows. And as a consequence, you will be able to get all our courses at a low price. If you want to access our LinkedIn network to get the discounts, just go to LinkedIn and search on LinkedIn for this link, which would be data.bootcamp with this code. It would be data.bootcamp and this code. With this, you will find our profiles. We recommend you follow us or add us to your contact network so that every time we publish discounts on our courses, you can get the discount code. Remember that we also publish training opportunities or vouchers to obtain the certifications for free. Thank you very much for accessing this course. If you want more information, you can find us on the Udemy forum and on LinkedIn. And if you have any questions regarding the Udemy platform, do not hesitate to contact Udemy support to solve your doubts. Thank you very much and see you throughout the course.
Welcome to this introductory model on large-scale language models. Through this course, we will not only learn about what they are, but we will also delve into their features and applications. In recent months, there has been a lot of discussion about these models, particularly with the emergence of ChatGPT, which has raised questions about whether they present a great opportunity or a significant threat. While it is true that these language models are highly useful tools for automating a wide range of tasks and generating content, they also carry certain risks that we will thoroughly analyze during the course, along with their limitations. On the topic of benefits, we have already witnessed how they are revolutionizing various aspects of users' lives. For instance, IBM recently announced that it has ceased hiring staff for certain positions that can be filled by this language model or ChatGPT. Additionally, it is expected that these advancements will impact in a significant number of creative jobs. Even the most traditional sectors are adopting these technologies. Mercedes and Microsoft, for example, have begun implementing ChatGPT in vehicles, with the expectation that this implementation will be successful in the coming months. Consequently, despite the risk involved, the applications of this model are expanding to numerous industries. So, why should we pay attention to these technologies now? Large-scale language models are not new. They have existed for years, including models like BERT. However, what has changed is the quality of this model. In the past, tuning and adapting language model for specific use cases required extensive manual work. For example, if you wanted to analyze product reviews to determine their sentiment, positive or negative, you had to make manual adjustments. Today, thanks to the advances in constructing and fine-tuning this model, it is possible to provide them instruction in natural language and have them perform useful tasks with minimal human intervention. This is attributed to two primary factors. Firstly, the accuracy and effectiveness of the models have reached a tipping point, enabling a wide range of applications. Secondly, the technology has become more accessible through the ability to instruct it using natural language. Moreover, there is an increasing availability of high-quality data and tools. Previously, building something with large-scale language model meant searching the web for clean datasets and essentially starting from scratch. However, nowadays there are numerous open datasets and high-quality open-source models that we can utilize for specific use cases. Additionally, we can access cloud services that provide GPUs for training and optimizing these models for particular use cases. In summary, while the underlying technology of large-scale language model is not new, they have recently reached their peak with significant improvement in both model quality and accessibility. Therefore, their application has recently become widespread across various industries. In this task, we will analyze in detail what a large-scale language model is. A large language model is a statistical model that aims to predict words in a text. The prediction is formulated as a statistical problem. If I provide you with some words, such as the beginning of a sentence but not its end, you could predict the missing words. This type of prediction is something that we have been doing in machine learning and statistics for a long time. There are numerous ways to fit a model to the data and predict these words. However, in recent years, we have developed methods that can achieve increasing accuracy, particularly as more data is introduced. This ability equips the model with the capability to learn useful information about the world. To give you an idea of the scale of these models, an individual can read about 700 books in their lifetime. However, a large language model is trained with trillions of data points. This volume of data is something that we, as humans, cannot handle. A simple use of these models would be to predict missing words in a sentence. For example, avocados are. The model could predict something about avocados, such as their color. It might indicate that they are likely to be green rather than blue, even though the model learns the probabilities of words. It doesn't truly understand what an avocado is. However, the model can deduce that avocados are delicious and not intelligent. Taking this ability to the extreme, specific text can be generated, such as a song about the sunset or data classification. This knowledge is acquired from the analysis of a vast amount of data, which is why they are referred to as large-scale language models. Initially, when ChatGPT was launched, the model responded to user questions based on the prompts provided. However, thanks to the development of additional libraries and tools like LangChain, these models have evolved and acquired additional capabilities. For instance, we have ChainCrow, a large language model based on ChatGPT that utilizes additional language models and tools like LangChain. This model is trained with databases related to chemistry and can answer specific questions regarding to the development of certain chemical compounds, methods of obtaining molecules with specific characteristics, and more. If a user asks how to synthesize a particular molecule, explain a specific chemical mechanism, or identify similar molecules, this model can access knowledge bases it has already learned from and utilize LangChain not only to directly respond to the user, but also reason or generate an action plan. Based on this action plan, it has access to a range of tools that allow it, for example, to search for additional information on internet, access complex mathematical tools, use them to obtain a result, analyze that result, and generate a final response for the user. Therefore, although large language models were initially designed solely to answer user questions based on their trained knowledge, these models now possess much more advanced capabilities. They can leverage a range of tools APIs and additional libraries like LangChain to conduct searches, gather additional information, and generate complex processing plans. In this task, we will explore the two different types of large language models that exist and review the development process of the ChatGPT model. There are two types of large language models, a base model and instruction following optimized model. The base model predicts the next word based on the training data of the text. For example, if we provide it with a sentence, the base language model can complete it. Even if we ask it about the capital of France, it can add relevant words related to the original questions. In short, it relies on probability to determine the word or set of words that are most likely to follow in the given context. On the other hand, the optimized model is specifically trained to follow instructions. These models are designed to respond to almost any given instruction. For example, if we ask the ChatGPT model to provide 3 ideas for cookie flavors, it will generate those ideas, such as chocolate, matcha, or peanut butter, instead of simply completing the sentence. How do we obtain this second type of model that can respond and follow instructions? It requires an additional training process of the base model. To transform the base large language model into an instruction following optimized model, we need to train it with significantly more data. Firstly, we proceed with the fine-tuning. This involves providing a series of examples where the desired output follows a given instruction. This allows the model to learn how to respond in a specific way to a given instruction. Additionally, we gather human ratings on the quality of the model's results based on different criteria such as usefulness, safety, honesty, and correctness of the answers. Next, we adjust the large language model to increase the probability of generating higher rated results. This is done through reinforcement learning from human feedback. This process was precisely followed to develop the ChatGPT model. The development of ChatGPT model involved three phases. In the first phase, supervised learning was utilized, where a set of prompts was provided and a human labeler responded to each prompt. Using this dataset, the existing GPT 3.5 model was fine-tuned. After completing the first phase, a reward model was created. A prompt was given, and the model generated different responses to that prompt. These responses were ranked by the human labeler, indicating the best and the worst ones. This process results in a reward model capable of evaluating the quality of responses. Finally, with the fine-tuned GPT 3.5 model and the reward model in place, the existing model was further improved. Using a new prompt, the optimized model was initialized to generate a response. The reward model was applied to evaluate and classify the response. Based on that evaluation, the model was asked to generate a different response for the same prompt, and the reward model was used again to assess whether the new response was an improvement over the previous one. This iterative process led to the enhancement of the optimized GPT 3.5 model. This process describes the development of the ChatGPT model, which consists of a base large language model and the instruction following optimized model generated through the aforementioned process.
Welcome to this Generative AI module. Throughout this module, we will learn about the different types of models that make up generative AI and how each of these models works. So, what is generative AI? Well, generative AI or generative models are nothing more than artificial intelligence algorithms that can generate new content based on existing data. This data can be unstructured data such as text, audio files, or even images. These models use machine learning techniques and data training to create new content. The importance of generative AI models lies in their ability to produce new ideas, automate tasks, and, in a way, push the boundaries of creativity. Here we have an example of an image created entirely with a generative AI model. In fact, different venture capital firms have already invested over $1.7 billion in generative AI solutions in the past 3 years. Furthermore, investment in this type of model is expected to continue growing in the coming years. Therefore, we can get an idea of the great potential these generative AI models hold. And what are these generative AI models? Well, two of the most well-known generative AI models to date are ChatGPT and DALL-E. Both ChatGPT and DALL-E are among the most popular models. ChatGPT is a chatbot that uses generative AI to produce human-like responses when a user asks a question or gives it a task. It was developed using the GPT-3 language model and has gained significant attention for its ability to generate impressive and sometimes very human-like responses. It can even incorporate a humorous tone into its answers. On the other hand, DALL-E is an image generation system that can produce original images based on text prompts. It has gained tremendous popularity in recent years and has been used to create over 2 million images per day, with over 1.5 million users. Both models were developed by the same company, OpenAI, and to this day, they are two of the most widely used models. Lastly, we have other models that, although less known, are also very useful, such as Stable Diffusion, DreamVault, and Mediator. Although they are less renowned, they have also been extensively used and allow for generating a wide range of content. Stable Diffusion is an open-source deep learning model that uses text descriptions called prompts to generate images of fictional scenes. DreamVault enables users to insert their own images, subjects, or characters into desired scenes. And finally, Mediator creates a fictional image based on the prompts provided. Here we can see an example of the results obtained using these three tools. On the left, we have the image developed by DreamVault. In fact, this image recently won a significant content creation competition. Then, on the top right, we have an image generated with Mediator, and below, an image generated with Stable Diffusion. As we can see, the quality of the results from these tools is astounding. If we wanted to use any of these tools, we can simply access their official website. This would be the Stable Diffusion page, which provides us with more information on how to use it and what it does. Additionally, it's worth mentioning that this tool is open source and free to use. In fact, there's no need to even register to use it. We can directly access it from here. Let's instruct it to generate a realistic picture of a green cat and see what result we get. Here it is. We can see that the images are of very high quality, especially this one, which looks really cool. We can zoom in, and by simply clicking Save As, we could download the image for ourselves. Next, another tool would be DreamVault. This is the official GitHub page of DreamVault, where we can find all the information about how the model works. We can see that we need to provide input images, and thanks to DreamVault, we can transform the characters or elements in the input photos, in this case, a dog, into the desired scenario. Here, we're going to ask it to send the dog to the Acropolis, and here we have the dog in the Acropolis. In the swimming pool, we can see how it generates a very realistic photo of the dog in the pool. With this model, we don't create images out of thin air. Instead, we provide a character and indicate how we want it to appear, and it is capable of generating it. Here we have more information on how it works and how to use it. Finally, we have the ToolMe journey, which can be used through the Discord forum. It used to be free, but now it is a paid service. Here we can access the community showcase, where they display examples of images generated by users. This tool creates images based on user texts and prompts, without the need to provide an input image. Here we can see the results of some photos. As we can observe, they are highly realistic, well-executed images with great quality. Now that we know more about what generative AI is and the different tools based on generative AI models, in the upcoming tasks, we will delve deeper into these models and also understand how they work. In this task, we will explore the differences between discriminative models and generative models. Let's begin with the distinction between discriminative models and generative models. It is important to understand the counterpart of generative AI, which is discriminative models. Traditionally, data scientists have worked extensively with discriminative models. The goal of these discriminative models is to identify whether a given observation belongs to Class 1, Class 2, Class 3, or any other class. One of the simplest examples would be identifying whether a particular image is a cat or a dog, as in this case. To achieve this, the discriminative model analyzes the distinguishing features of each group. On the other hand, generative models represent an advancement in the field of artificial intelligence, as they have the potential to create new information based on input data. For example, if we provide a generative model with a dataset, it can generate a new image of a cat that is different from the provided images. Here we have an example where the model is learning from input images and is capable of generating new information through generative AI. As we can see, there are many differences between discriminative and generative models. Discriminative models utilize existing features to differentiate, whereas generative models create new information based on what they have learned from the training dataset. In this task, we will learn about the different types of generative artificial intelligence models. There are several types, each with different approaches and applications. We have three main groups. Firstly, the GANs, an acronym for Generative Adversarial Network Architecture. We will detail each of these architectures later. Secondly, we have transformer-based models, which are widely used for natural language processing. Finally, we have the variational autoencoder models, also known by the acronym VAE. Throughout the upcoming tasks, we will delve deeper into each type of model. We'll start with the GANs, which stand for Generative Adversarial Network. This is a type of deep learning model used to generate new data similar to the training data. GANs have been effectively used for various applications such as text generation, musical composition, and image synthesis. Regarding the architecture, GANs consist of two neural networks, the generator and the discriminator, which work together to find a balance between the two networks. The generator network creates new data that resemble the source data, while the discriminator network differentiates between the source and the generated data to recognize what is closer to the original data. In this scenario, we would have input data, which would be a vector, and the generator network. This generator creates new data similar to this input data and passes it to the discriminator network. The discriminator network uses the data generated by the generator along with real examples. And through a classification model, it determines whether these generated data are similar to real ones or are fake. With the feedback provided by the discriminator neural network, the generator neural network improves its ability to generate new data that closely resemble the real data. Eventually, the generator is capable of producing high-quality new data that closely resemble the input data. Thanks to this, it generates new data that resemble the data it has been trained on. As for their use, GANs are commonly utilized in tasks of generating images and videos. These models have shown impressive results in generating realistic images, creating animations, and even generating synthetic human faces. Here we would have an example of an image entirely generated using GANs. In this task, we will delve deeper into transformer-based models. As we previously mentioned, transformer-based models are primarily used for natural language processing tasks. The transformer model uses a self-attention mechanism to attend to all words in the input sequence simultaneously, thereby capturing long-range dependencies and context more effectively than traditional natural language processing models. Now, we will attempt to briefly explain the architecture of a transformer in simple terms, keeping in mind that it is a rather complex structure. In the architecture of a transformer model, we have two main components: attention blocks and encoding layers. The attention blocks represent the model's capacity to focus on different parts of the text. If we examine a sentence, some words may have more influence on the meaning than others. The attention blocks aid the model in identifying these keywords and understanding their interrelations. On the other hand, the encoding layers serve as layers of knowledge. Each layer in the transformer model learns something new about the text. For instance, in the first layer, the model might learn about the basic sentence structure, while subsequent layers might learn about word meanings and more complex relationships. The transformer model processes and comprehends the text by moving through several encoding layers and utilizing attention blocks in each one. As the model advances through the layers, it captures increasingly complex and deeper information about the text. Once the model has processed all the layers, it can use this accumulated knowledge to perform specific tasks, such as text translation. We can illustrate this with an example of transformer architecture. We can observe two distinct blocks, the encoders and the decoders. The encoder processes and comprehends the source text, capturing its meaning and structure. It then relays this information to the decoder. The decoder uses this information to generate the desired output, translating the input text in the case of translation. Both components work together to transform the input text into a meaningful outcome. It's also worth mentioning that the encoder and decoder share similar structures in terms of attention blocks and encoding layers. However, as we previously mentioned, their roles differ. The encoder's aim is to understand and process the source text, whereas the decoder uses the provided information to generate the output. So, what do these components comprise? We have a simplified schema of the encoder and decoder structures here. It includes the previously mentioned attention layer, along with the encoding block. As we noted earlier, both the encoder and the decoder share similar components, namely the attention layer and the encoding layer. As we previously stated, one of the most common uses of the transformer model for generative AI is language translation. Thanks to its ability to discern patterns and complex linguistic nuances, the transformer model serves as a powerful tool for generating high-quality text in various contexts. Therefore, transformer models are employed for tasks related to natural language processing, such as language translation, text generation, and summary generation. As we can intuit, the capabilities of working with text in ChatGPT are primarily based on these transformer models. In this task, we will focus on explaining variational autoencoder models, also known by the acronym VAE. The VAE model uses a neural network to encode input data into a lower dimension representation. This representation is then decoded to generate new input data. To develop a condensed representation of the data, known as the latent space, a specific type of neural network is trained on a dataset. This latent space can then produce new data that is comparable to the original data. Here, we have an example of the architecture. We take some input data and use an encoder, as we did with the transformers, to reduce this data into a smaller representation, known as the latent space. Then, the latent space goes through a decoder that generates the output. The variation that allows for the generation of new results similar to the input data occurs when transitioning from the latent space to the decoder, moving from smaller to more comprehensive information. These models, like GAN models, are typically used in applications such as text, audio, and image production. They are especially effective in creating new content. However, they can also be applied to other tasks, such as anomaly detection and data compression. We have an example here where these VAE models have been used to generate new images from data. As we can see, they have generated images similar to the original one, but with variations. Now, let's explain this concept of latent space in VAEs better. The term latent is derived from the Latin word for to lie hidden. It refers to the process of simple dimensionality reduction while preserving the maximum information. We will use another example of dogs and cats to understand it better. We aim to reduce these images into points. Depending on the image size, there will be thousands of data points for each of these images. These points need to be reduced in such a way that they remain representative of the original images. In the latent space, similar images, represented by a series of points, should be close to each other. Here is an example with images of cats and dogs. If we convert these images into points, these points will need to condense the most representative information of these images so that the images of cats in the latent space are grouped together, and the images of dogs are also grouped together. Both categories should be easily distinguishable. This is what is aimed for when generating this latent space. How is this idea of latent space used in generating new images? Small manipulations in latent spaces lead to different images. The manipulation should be optimal enough to keep the data point closer to its equivalent and move away from other types. Here we have an example where this idea of latent space is used to generate new images. The input images are shown here, and we are attempting to generate new images based on these with subtle differences. For instance, we want these images to transition closer to the blonde hair class. These models add small variations to the original images to approach this blonde hair class. What if we want to add glasses? We can see how the obtained image is quite similar to the original, but glasses have been added in this case. The same goes if we want to transition these images to men. We can see how there are small variations. In this way, we can better understand how VAE models work, thanks to the concept of latent space. In this task, we will briefly mention the challenges faced by generative AI. One of the key challenges in generative AI today is finding a balance between complexity and simplicity. On one hand, a model needs to be complex enough to capture nuances, but a model that is too complex can be prone to overfitting. This means it may perform well with training data but does not generalize well to new data. Therefore, it is important to find this balance between complex models that harness generative AI and models that do not. Complex models can learn a lot of information about specific tasks, while simplicity allows models to extrapolate to new tasks. Another challenge is the computational cost involved in training generative models. Many of these models require a significant amount of power and memory, making them difficult to scale with large datasets. For example, SafGPT's generative AI model has a daily cost of $700,000 in computing resources alone. Hence, there is a need to develop efficient models that are sustainable in the long term within resource-constrained environments. In summary, the main challenges in generative AI are finding the balance between complexity and simplicity, as well as optimizing models to reduce computational costs and improve maintainability in resource-limited environments.
Welcome to this module on tools for large language models and natural language processing. Through this module, we will learn about a variety of tools such as Hugging Face, OpenAI's IP for making HTTP calls, open source models, and LangChain. We will begin by describing these tools, or at least some of the most important ones in natural language processing. Firstly, we have Hugging Face Transformer, a series of pre-trained deep learning models designed for the process of creating language models. They are accessible through the Face interface. This resource not only offers pre-trained models but also provides pipelines for direct usage, along with a range of additional functionalities to train and optimize these existing models. Next, we have NLTK library, a stalwart in the natural language processing that contains a data corpus for training natural language model. In addition, we have libraries like spacing and mapping. The spacing libraries encompass a series of resources that offer us datasets for training natural language models. We also have the spacing and Gensin libraries. These libraries bear similarities to NLTK. They are Python libraries that enable us to work with natural language models, each providing some additional features. For instance, Gensin included the word2vec function to convert a set of text into vectors. We then have the familiar OpenAI tool, which gives us access to the GPT model from Whisper and DALL-E through its API. We also have the Big Data library from Spark NLP, a resource designed for processing large volumes of text data with Spark, with a focus on natural language processing. Lastly, we have LangChain, a Python tool that facilitates the enhancement of large language model capabilities. Through this module, we will delve deeper into the most important tools we have just mentioned. In the next task, we will start describing the OpenAI IP to access the ChatGPT model. Welcome to this task where we will focus on explaining one of the tools for large language models, specifically the OpenAI API. The OpenAI API for ChatGPT is an interface that lets us integrate the GPT model into our applications, products, and services. The API offers a straightforward way to send requests to the OpenAI platform and receive responses generated by the ChatGPT model. Please note that the use of the OpenAI API is subject to certain limitations and involves a cost per request. Furthermore, it is vital to adhere to the policies set by OpenAI regarding to the ethical and responsible use of this technology. How can we access this API? As we note, it is a paid API. We need to provide credit card details through the official OpenAI platform. Once we have added a payment method, we will navigate to the API case section. It is simple as create new secret key, which automatically generates an API access key for us. The operation of this API is based on HTTP request. We send a POST request to the OpenAI API with the necessary parameters. These parameters can include the input text or the model to be used. For ChatGPT, we can specify an initial message or an entire conversation, including user message and model responses. These functions, like a conversation history, providing context for the new question. Here, we provide an example of a call made using Python. As we have mentioned, we need to set the model to be used, in this case GPT 3.5, as well as the question to send to ChatGPT. Additionally, we can send contextual information. In this case, the context is provided as a conversation history, giving more information to the model. Finally, we have the request to the model. Once the request is made, ChatGPT processes the entire input and generates a response. This response is returned as part of the HTTP response, and we must extract it and use it on our application or service as needed. It is important to note that the output doesn't just provide the response to our question, but also additional information. To access this additional information, we must make a selection within the message content, which contains ChatGPT response. Furthermore, the OpenAI API also offers extra options, such as the ability to set the temperature, a parameter that controls the randomness of the model responses. We can also specify, for example, the maximum number of tokens in the response from ChatGPT, allowing us to control the response length. Now let's look at exactly where to get the API key. As we have mentioned, we must visit the OpenAI platform and register. Once we have registered and logged into our account, we will have access to the API keys section. To access these API keys, we must have previously set up the payment method. Once that's done, we can generate a new API key. It's as simple as naming it, clicking create, and the key is automatically created. To revoke it later, we simply click on Revoke Key and access will be lost. Additionally, OpenAI provides us with more information about our usage and call statistics. It also enables us to set limits to prevent excessive use. We can establish restrictions in the billing section. By navigating to the usage limit, we can see how to set two limits to ensure that we don't exceed our desired amount. To learn more about the API, we can go to the API reference section, where we will find additional information about the API, how to use it, make calls, access variables, list models, and all the necessary information to customize the call through the API. I would also like to mention that there are different ways we can use the ChatGPT model. One way is for it to complete the prompt we send. For example, we might send a prompt and want it to complete the sentence. It can also be used in a chat format, where we pass a list of messages, construction a conversation, and the model will provide a response. In this case, we need to use the chat version. We pass a message and the model will respond based on that conversation. We can also use the model to edit specific information or instructions. For instance, we might pass an input sentence and ask the model to correct the grammar. The model can also interact with images. We can ask the model to generate an image, provide a prompt describing the image, and the model will return that image. The model can also edit an image using the Create Image Edit function and generate a variation with the Image Variation function. All these image-related functions are currently in beta. Finally, we have the embeddings functions. We pass an input text to the model and it will return a numerical vector that can be consumed by a machine learning models for predictions. We pass text to the model and it will return a numerical vector. It's also worth mentioning that OpenAI has integrated new functionalities for audio, similar to the image functions, which are also in beta. These include translation functions, such as audio translation function, and a fine-tuning function for adjusting the model. As we have seen, this API is incredibly versatile, offering many functionalities which can be used to easily integrate these functionalities and capabilities of ChatGPT into any of our products or services. In this task, we will learn more about Hugging Face tool. Hugging Face is a company dedicated to artificial intelligence and natural language processing. It has distinguished itself by developing advanced tools and models in this field that have made significant impact. Specifically, Hugging Face has carried out a project focused on designing tools for the use of artificial intelligence. In particular, Hugging Face is known for its open source platform called Transformers. This platform provides a wide variety of pre-trained deep learning models specializing in tasks of natural language processing. These models have been trained on large datasets and are designed to perform tasks such as text compression, language communication, or sentiment analysis. Hugging Face Transformer platform has been broadly adopted by developers and companies, offering an accessible and efficient way to use the latest natural language processing models. Users can take advantage of these pre-trained models to build NLP-based applications without having to train models from scratch, thus saving substantial time and resources. Besides the Transformers platform, Hugging Face has also developed other software tools and libraries in the field of natural language processing. Their open source approach encourages collaboration, allowing the scientific community and developers to continuously contribute and improve the available models and tools. How does the Hugging Face tool work? Imagine that Hugging Face is a large warehouse full of deep learning models. These models are at the forefront of natural language processing and have, in fact, been created by data scientists from major tech companies such as Google, Microsoft, and Amazon. This means that if you are a data scientist or someone looking to advance in this field, you can go directly to Hugging Face and explore all these models for your own use. But Hugging Face also offers the opportunity to learn more from the best. At Hugging Face, you can not only use their models, but also explore their architecture and see how they operate internally. This provides the opportunity to understand how their algorithms and techniques have been developed, and gain valuable insight into how these models are built and trained. In summary, Hugging Face is not just a warehouse of cutting-edge learning models, specializing in natural language processing, but it has also become an essential resource for professionals in this field. It provides access to powerful and advanced technologies, as well as the opportunity to learn from the best in this field. Therefore, it is an essential tool to understand if we want to work with large language models. We will now briefly explore this platform, so we won't delve too deeply as we will investigate this platform more thoroughly in the Hugging Face module. To access Hugging Face, simply search for huggingface.com and you will reach the official platform. Here we can see that it has different sections such as models, datasets, documentation and solutions. If we go to the main page, they highlight the features of this platform. They tell us that it is being used by a wide variety of organizations such as Grammarly for text translation. Then they suggest that Hugging Face is an account for collaboration and discovering machine learning models in a collaborative manner. They also point out a series of tasks and use cases they aim to solve with their models, some focused on audio, vision, or language. They then talk about their transformer library, which, as we have already mentioned, in this one of the key libraries developed by the Hugging Face platform. This library allows us to work with natural language processing models and related functionalities. It is very easy library to use and install and is used through Python. They also indicate that it allows us to obtain predictions through their API, which enable us to use deep learning models very easily without having to worry about installations or servers. We simply call their APIs to use them. Then they talk more about the platform's development and its contributors. Let's go to the top platform and see how they offer a wide variety of models in this model section. We have the various model filters, the sections, and the list of models. We can see at a glance that there are hundreds of thousands of models. The dataset section gives us access to different datasets that we can use to train models. Just like before, we have a filter section and the list of datasets. In Spaces, they show some of the apps that have been developed with the models. We have the Docs section, here where we can access very specific documentation related to this field. The Solutions section shows us the different solutions the company has developed, and a Pricing section for access to more advanced features. As we can already infer, Hugging Face is a key tool for working with large language models, and we will use these tools in the upcoming modules. In this task, we will briefly explain what LangChain is. LangChain is a tool that helps us create programs that use language models. LangChain makes these programs more powerful by connecting them with other sources of information and enabling them to interact with other environments. It is written in Python programming language and is designed to be easy to use and highly intuitive. With LangChain, we can leverage the power of large language models and combine them with other sources of knowledge, computations, or programs to create truly innovative and transformative applications. Therefore, it is a key tool if we want to work with large language models. So, how does this tool work? The main idea of LangChain is that it can link different components to create more advanced use cases using large language models. And what are these components that it allows us to link? Well, within LangChain we have different components. On one hand, there are prompt templates. These templates are for different types of prompts, such as chatbot style templates, question and answer templates, LE5 style templates, etc. Then we have the component of large language models, which allow us to link with different language models such as GPT-3, Bloom, or even models from Hugging Face. Next, we have the agent part. Agents use the large language models to decide which actions should be taken. Tools like web search, adding a calculation tool, or other different tools can be used. With agents, we can expand the capabilities of large language model to autonomously perform web searches, for example. Finally, we have the memory module. This memory module allows large language models to have both short-term and long-term memory. For example, with this module, we can modify a large language model to store past conversations with the user, allowing it to recall past information provided by the user and provide more detailed responses based on that information. LangChain has multiple components that allow us to enhance the functionalities of our large language models. Now, let's briefly explore the LangChain platform, as we will delve much deeper into this tool in the upcoming modules. The official LangChain page can be found on GitHub. This is where the library is hosted and where we can find more information or install it. It provides instructions on how to install it, as it is a Python library using pip install LangChain. It also provides further information about the QA part, chatbot generation, and the agents we mentioned earlier. It indicates that components we mentioned before, and there are additional components such as data augmented generation, which is quite new, evaluation, which is also in beta, and the change component that we will delve in the upcoming task. From here, we can access more information, and they also have a documentation platform where we can access the documentation for the entire platform. It includes an introduction, installation information, a quick start guide, and detailed information about the different modules it contains and various use cases. If you have any questions on how to use this tool, we recommend accessing this platform to find the answers. In this task, we will discuss various large language models. One of the most renowned and popular language model is ChatGPT, developed by OpenAI. However, this model is not the only one available. In fact, over the past few months, more than 100 language models have been developed. Numerous large language models, both proprietary and open source, are at our disposal. Each of these models is unique, having their own strengths and weaknesses. The provided chart illustrates an array of large language models available. While it is not an exhaustive list, it highlights some of the most significant ones. For instance, the Pythia model is relatively small and licensed under the Apache license, which means it's open source. The chart shows the creator of the model, its launch year, and provides more information about this model, which is actually a collection of 8 different models of varying sizes. Generally, the smallest models tend to be the least powerful, as the largest and most powerful models are trained with larger datasets. Next, we have Dolly model, also open source, developed by Databricks. It's based on the Pythia model, but optimized through the fine-tuning process. Then we have GPT 3.5, which serves as the foundation for ChatGPT. Developed by OpenAI, it's a proprietary model, meaning its code is not openly available, and its usage incurs a fee. As we already know, various versions of ChatGPT exist. Following this, there is the Opt model, launched by Meta, based on GPT-3 architecture. We have Bloom, a model specialized for working with different languages. Then there is GPT Neo, developed by the same group that created Pythia and based on the GPT-2 architecture. We also have the previously mentioned BART model developed by Meta, which evolved from the original BERT model developed by Google and was inspired by the GPT model. The T5 model, very similar to BART, was developed by Google for 4 languages. Lastly, we have the BERT model, one of the pioneers, launched in 2018 by Google. One could argue that BERT was the precursor of these weights and the subsequent emergence of large language models. As seen in the previous table, most models are open source, with the exception of OpenAI's GPT model, which is proprietary. Why is using open source model interesting? Open source in the context of large language model refers to the availability of a model for use, modification, and public distribution under an open source license, meaning we can use this model at no additional cost. Open source large language model also employ machine learning techniques, specifically neural networks, to understand and generate natural language text. Ultimately, the distinction between a proprietary large language model like GPT and open source model is that open source models are openly available. We can use them freely, adapt them to our specific use cases, and they don't entail any usage fees. Additionally, their code is shared in a public repository, typically on GitHub or Hugging Face. Why are these open source models important? Firstly, these open source language models are accessible to everyone, fostering innovation and cost savings in licensing. Their open nature also encourages collaboration, accelerating the development of these technologies. They also allow for customization for specific use cases. For example, we can utilize one of these models, such as Dolly, adapt it to a business use case, and optimize it for better performance in our specific use case. We will only need a dataset related to our use case to optimize these friendly, accessible pre-trained models. They also generate more trust as they allow us to understand how they work and how they have been trained, this preventing biases or ethical issues. As we have just seen, these open source language models have significant advantages compared to proprietary models. Depending on our needs and the use case we want to develop, it might be preferable to use these open source models.
Welcome to this open source large language models module. Throughout this module, we will learn about different open source large language models, their differences, and which ones are the best. Although ChatGPT has made a significant impact in the world of technology, it is important to note that ChatGPT is not an open source model. This means that we cannot modify its source code as it is not publicly available, nor can we use it for free since there is a cost associated with using the model through its API. In contrast to proprietary models like ChatGPT, there are open source models available. These models offer several advantages over proprietary models, such as data privacy, customization, affordability, and democratization. When it comes to data privacy, many companies prefer to have control over their data and are obligated to keep it secure without sharing it with third parties. Using ChatGPT can pose serious privacy issues because, as mentioned before, ChatGPT uses user data to send it to a server for retraining the model and performing analytics to allegedly improve the code. This violates the privacy of company data. One of the advantages of open source models is customization. Open source models allow developers to train the models with their own data and even add filters to have control over their data. This enables us to personalize the chatbot with our information and optimize it for specific use cases relevant to the company. Affordability is another advantage of open source models. Open source models are freely available, eliminating the need for a significant investment in hardware to train the models. They come pre-trained, so optimization can be achieved with fewer computational resources, resulting in lower costs. Finally, open source models contribute to the democratization of artificial intelligence. These models, being openly accessible, provide opportunities for future research and development to address various artificial intelligence challenges. Therefore, open source models offer several benefits that proprietary models like ChatGPT do not provide. Additionally, integration is an important consideration. Many companies might initially think that developing an open-source large language model is more costly since it requires investing in computational resources and specialized personnel. However, this is not entirely true, especially when there is intensive use of such models. A recent study conducted at the Institute of Information and Technology of the University of Madrid in 2010 examined a language model used for creating these types of models. According to this study, for a low range of daily requests, around thousands of requests per day, models like ChatGPT are more cost-effective than open-source large language models. However, for millions of requests per day, which are not a high number and easily achievable by a company, open-source models become much more cost-effective. This can be clearly observed in the graph. On the vertical axis, we have the cost, and on the horizontal axis, we have the usage. The orange bar represents open-source models, while the blue bar represents ChatGPT. When the usage is limited to a few queries, the cost of ChatGPT is significantly lower than that of open-source models, falling within this range. This represents the cost of ChatGPT, while this represents the cost of open-source models. It becomes much more expensive to use open-source models when the number of requests increases. However, for moderate usage of these models, we can easily operate within this range, where the cost of open-source models and proprietary models like ChatGPT is similar. However, when these models are used on a daily basis, implemented company-wide, and widely used by employees, the difference becomes significant, and the distribution is reversed. It becomes much more costly to use ChatGPT compared to the cost of developing and optimizing open-source models. While optimizing open-source models may require initial effort, their usage cost remains stable regardless of the extent of usage. On the other hand, the cost of ChatGPT escalates significantly as its usage expands within the company. Therefore, if sporadic use of such models is required, proprietary models may be suitable. However, for daily and standardized usage of these models, it is much more cost-effective to develop and utilize open-source models. Now let's try to put some numbers to the cost of using ChatGPT. As we know, ChatGPT's API is paid and costs approximately 2 cents per 1,000 tokens. Each token roughly corresponds to 3/4 of a word. So, if we process 1,000 small text snippets per day, which would be around 500 words or 667 tokens, the cost would be $1.30 per day. At first glance, this may not seem like much, but what happens if we process 1 million documents like that every day? Let's remember that 1 million is not excessive, it is a normal usage scenario. In that case, the cost would be $1,300 per day because we would multiply the previous cost by 1,000, resulting in a daily usage cost of $1,300, which translates to approximately $500,000 per year. Therefore, when limited usage of ChatGPT is involved, the cost may be affordable. However, when normal and standardized usage is implemented in a company, the cost becomes exorbitant. In such cases, it is more cost-effective to train our own open-source model rather than relying on ChatGPT. In this task, we will discuss the different open-source language models currently available on the market. Today, some of the well-known open-source large language models include Llama, Alpaca, based on Java, Vicuna, and GPT-4o. For example, Llama was one of the first models developed by Meta and served as a starting point for many other models. It incorporates conversations with users, and through these interactions, the Llama model was enhanced to create Alpaca. Through conversations with users, the Java model was developed, leading to the creation of Vicuna. Next, we have GPT-4o, a community-driven project in a model trained on a massive corpus of interactions obtained from assistants like ChatGPT. It is further trained with additional information such as code and chat data, including cover flow and various sources. GPT-4o is widely adopted and can be easily used in a local environment. Another model is Raven, an open-source chatbot that produces results similar to ChatGPT. We also have OPT, developed by Meta, which stands for Open Pre-trainer Transformer Language Model. Although not as good as ChatGPT, it has demonstrated considerable capabilities, especially in zero-shot or fused prompting scenarios where there are few or no examples available. Next is the FLAM T5XXL model, which has been optimized with over 1,000 additional tasks. It undergoes fine-tuning to improve performance across these tasks. In these additional tasks, FLAM T5XXL outperforms more generic models like ChatGPT. Here is a summary of some of the most important open-source large language models available today. However, the emergence of these open-source models is just the beginning. In recent months, there has been a rapid development of new models, variants, and an increasing number of options that can rival ChatGPT in performance. Here are a few more models, distinguished by the type of license. They are all open-source licenses, but some models can be used for commercial purposes, as shown on the right, while others are developed for research or non-commercial use. Additional models include Colossal Chat, which integrates the development phases used for ChatGPT, including reinforcement models. There are also models developed by companies like Databricks, such as DALL-E and its variants like Alpaca and Alpacalora. Lastly, there are newer models like FAISS, Koala, DALL-E, and Lidiama, which are not widely known yet. For those models that can be used commercially, shown on the right side, NanoGPT and OpenChatKit are options, although they are not widely known. Nano T5 is also available, and all of these models can be used for commercial purposes. As we have seen, the emergence of new open-source large language models is just the beginning, and the options continue to grow. Which model is good? How much data should be used to achieve reasonable performance? These questions were addressed in research conducted by OpenAI and Google. These companies documented several studies indicating that large language models with tens of billions of parameters started to exhibit capabilities comparable to human performance. In the graph, we can see the initial models with only 1.3 billion parameters, which did not perform well in terms of precision, represented on the vertical axis, regardless of the context or examples provided. The maximum performance achieved was around 5%. However, when we move from 1 billion to 10 billion parameters, the situation changes significantly. Initially, with a few examples, the performance still falls short, but as we apply fused prompting techniques, these chatbots improve their performance. The maximum performance achieved in these scenarios is around 25%. However, when we make a qualitative leap from tens of billions to hundreds of billions of parameters, the landscape changes considerably. Models can achieve performance exceeding 60%, comparable to human-level performance. These models can learn a lot from a single example. Therefore, among the different options of open-source large language models mentioned earlier, those with over 170 billion parameters can be expected to perform very well. Hence, one criterion to consider when selecting an open-source large language model is the number of parameters it has. Additionally, there is a useful tool that provides insights into the current best-performing open-source large language models. By following the link to the presentation, it redirects to the official benchmarking page where the results are showcased. The evaluation methodology employed ELO ratings, which allowed users to vote on the model's performance. The same prompt was given to Model A and Model B, and users directly voted for the better one. Users from around the world participated in the voting process, covering different languages and prompts, resulting in the rankings. In conclusion, we cannot definitively state that one model is better than others across all tasks. However, we can gain a general idea of which models perform better overall, and then it becomes a matter of testing each model in specific tasks and selecting the one that performs best for a particular use case. In this task, we will delve deeper into the open-source large language models derived from Llama. Llama was the first model to emerge. After Llama, Alpaca was developed as an optimized version. Finally, in recent months, one of the most well-known models, called Vicuna, was released. Vicuna is also a model that originated from Llama. Let's start with the first model, the original Llama model. This model was developed by Meta, also known as Facebook, and it was one of the earliest open-source models to appear. It paved the way for many more open-source large language models. For many months, Llama has been the most efficient alternative among open-source models compared to proprietary models like StatsGPT. Despite being smaller than many commercial models, Llama has surpassed GPT-3 standards in various benchmarks. However, while it is open source, access to Llama is limited to researchers and comes with significant restrictions for commercial use. If we visit the official Meta webpage, we will find the announcement for the first Llama model. Here, they provide information about the model, indicating different sizes with 7 billion, 13, 33, and 65 parameters. They share insights on the model's applications, such as protein structure appreciation, as well as potential risks associated with the model. They offer access to the original paper, which is available here. The scientific article was the publication introducing the Llama model. Additionally, there is an application form for access to Llama, redirecting to this form. As previously mentioned, the use of the Llama model is restricted to research, meaning we cannot freely use it for commercial purposes. We can apply for access using the provided form, or alternatively, we can access the Hugging Face environment, which also provides instructions on how to obtain the model. It states that we need to fill out the aforementioned form to download the model weights. Once obtained, we can use Hugging Face transformers to construct and utilize the model, with further instructions provided. If we prefer not to install anything, another option is to access the LM6 chat webpage, which we saw before. This platform allows users to evaluate different large language models by testing and voting for the model they find works best. Going to the Single Model section of the web page, we can find the Llama model. Selecting it, we can directly input a question to use the model. Let's test this model by making a request and seeing the result we obtain. Here, we can see the response generated by the Llama model with 13 billion parameters, and we can observe that it doesn't provide a satisfactory solution. We asked it to write a blog, but it didn't generate one. This particular Llama model, even though it is one of the more basic ones with 13 billion parameters, there are Llama models with many more parameters that are more efficient and perform better. In this case, we can see that although it can generate phrases, it doesn't fully understand what we are asking. Now that we have learned more about the Llama model, in the upcoming tasks, we will explore the Alpaca and Vicuna models in greater detail. In this task, we will learn more about the Alpaca model. As mentioned before, Alpaca is a model based on the original Llama model. It was developed by researchers at Stanford University and is an improved version of the Llama model, which is also based on the original Llama model. Alpaca was developed using over 50,000 demonstrations following the instructions of GPT 3.5. Researchers claimed that it produced comparable results to the OpenAI model. What's most surprising about this model is that it achieved very similar results to the OpenAI model. What's even more impressive is that it achieved similar performance to OpenAI but at remarkably lower development costs. It is estimated to have cost around $600 to produce and train the model, a significant reduction compared to the millions of dollars required to generate the OpenAI models. Like the Llama model, Alpaca is open source, although it comes with certain usage restrictions. It can be used for research purposes, but its commercial use is highly limited. More information about this model can be found in the publication released by Stanford University when Alpaca was launched. It states that Alpaca is an optimized model based on the 7 billion parameter Llama model, adjusted with an additional 52,000 demonstrations. The preliminary evaluation with a single instruction showed comparable performance to OpenAI's TXDaVinci 003 model. However, Alpaca is much smaller and more cost-effective to produce, with a cost below $600. Further details about the model and its training process are provided. Initially, a set of instructions was generated to train TXDaVinci, resulting in an additional 52,000 instructions. Using these additional instructions, the Llama meta model and supervised fine-tuning, the first Alpaca model was developed. Currently, there are many versions of the Alpaca model. The Alpaca 7B is the original model, but there are now many more models available. The preliminary evaluation is also discussed. It responds without difficulty to a series of questions. It even correctly writes an email when requested. However, the researchers acknowledge the limitations. For example, when asked about the capital of Tanzania, it provides the correct answer but mentions that it changed in 1974. From then on, it was Dodoma, so it would not be responding accurately. It can also utilize incorrect information to answer questions as if they were true. More information is available, including access to a demo, optimization instructions, data generation details, and access to the model published on HumanFace. If we visit the original GitHub page, we can find more details about the model and instructions on how to use it, including generating input data. All the information about the model is provided. Although initially believed to be a significant competitor to OpenAI models, Stanford recently withdrew its model due to reported hallucinations, security concerns, and cost issues. As the researchers themselves state in their publications, this model is not exempt from the limitations that many large language models have, such as hallucinations, fabricating information, or responding incorrectly. Nevertheless, the appearance of Alpaca represented a significant leap forward, achieving performance similar to DaVinci while drastically reducing the training cost of models. If we want to use this model, there are various ways to access it. By visiting HumanFace, we can find multiple versions of the Alpaca model. As mentioned earlier, there are many variants available now. It has been extensively used and optimized to generate numerous variations. We also have the native model with installation instructions and download files. Alternatively, we can revisit the LMSYS page and give it a try. Here, we can see how to use the Alpaca model and even compare the performance of the Llama model with the Alpaca model, highlighting a considerable improvement. Let's request both models to write a blog about interrail trips and compare their responses. We need to specify Llama for one of the models. Here, we can observe the difference in the responses. Let's ask another question, for example, about the largest mammal in Europe, in English so that both models can understand. We can see that Llama still struggles to comprehend the question, despite it being specific. On the other hand, the Alpaca model correctly responds that it is the brown bear. We can verify the accuracy of this response on the internet. Thus, we can easily observe the difference in performance between the Alpaca and Llama models. In this task, we will learn more about the Vicuna model, another model derived from the Llama model. Vicuna was developed by Stability AI and is a fairly recent model. The Vicuna 13B model is an open-source chatbot trained through fine-tuning with web data. They used conversations shared by users, which were collected using the SARE GPT tool. In a preliminary evaluation where GPT-4 was used as the judge, Vicuna demonstrated, in approximately 11 cases, an improvement in the response quality compared to OpenAI's ChatGPT model and Google's BAR model. It even outperformed other models of the same quality from Google. Specifically, in the case of Google's ChatGPT, the BAR model improved the quality of the response. Moreover, it surpasses its predecessors, such as Llama or Stanford's Alpaca. Additionally, training Vicuna costs around $300, which is approximately half the cost of training the Alpaca model. The interesting aspect is that both the code and weights are available, along with a publicly accessible online demo. However, like other models derived from Llama, its commercial use is limited. It can be used for research purposes but not commercially. Therefore, we can say that the Vicuna model is the heir to the Llama models and may establish itself as a reference model based on the original Llama model in the coming months. If we visit Stability AI's official page, the company that launched the Vicuna model, we can access the publication from April 28 of this year. It provides more information about the model, including its development, open-source nature, functionality, and evaluation results. We can see that this model performs significantly better in most of the tests conducted on these chatbots. For example, it surpasses Alpaca and other models like Koala. It's worth mentioning that there have been recent variations of Vicuna. Here, we can observe its superior performance compared to another GPT-4o model. From this link, it redirects us to where we can obtain the weights, explaining the process of obtaining them. If we go to the beginning, we can explore other products developed by Stability AI, such as Dream Studio, a data development tool. For further performance information, we can visit the LMSIS page and search for the Vicuna model. Here, we can already see that it is comparable to GPT-4 in terms of performance. They also provide access to the code, weights, and demo. What's interesting is that they compare it to previous models. In this case, comparing it to the Alpaca model, they ask both models to generate a blog about trips to Hawaii. We can examine the responses from each model and notice the strikingly different tone in Vicuna's response. It provides more details about the trip, uses colloquial expressions specific to the location, and talks about local food. This demonstrates that Vicuna's response quality is superior to its predecessors. To access this model, we can go to the official GitHub page. In this case, they suggest accessing it through the Fast Track platform, which facilitates easy installation of such models. Alternatively, we can use Hugging Face. In fact, on Hugging Face, there is a chat section that allows us to directly access the Vicuna model. And of course, we also have the LMSIS platform where we can access the Vicuna model. We can go to the Single Model section, select it, and choose between the 7B and 13B variants. The 13B variant has more parameters and thus performs better. We can then ask any question we want. For example, we can ask it to write a blog about trips to Europe and see the response it generates. With previous models like Llama, it couldn't even understand the question, and Alpaca had serious limitations when asked to write a blog, unable to adjust its tone based on our requirements. Here, we can see how the Vicuna model, when asked to write an interesting blog, can modify its tone and writing style accordingly. Therefore, we can conclude that Vicuna is a highly useful model with capabilities similar to those of Llama. Thank you for watching the video. In this task, we will learn more about the Koala model developed by the University of Berkeley. The University of California, Berkeley has introduced Koala, which is a new open-source large language model developed for research purposes. This model has been trained using the Llama language model and the Google language model. It utilizes the Llama language model from Meta and is fine-tuned with a high-quality dataset obtained from web dialogues, particularly focusing on responses to queries from other models such as ChatGPT. Hence, it has been trained on web dialogues, specifically from ChatGPT, consisting of over 70,000 dialogues, as well as dialogues from other models like ChatGPT. This model provides a lighter, open-source alternative to ChatGPT and includes a useful tool called EasyLM, which serves as a framework for training and fine-tuning this model. If we visit the official Berkeley page, where the article about the model was published, it states that they used the pre-trained 13 billion parameter Llama model, one of the largest, and further underwent an additional supervised fine-tuning process. This process involved using open data, such as ChatGPT dialogues and user interactions with other chatbots, followed by a selection of high-quality data. In other words, it was not trained on just any dataset, resulting in the 13B Koala model. Here we have information about the accessible demo to observe the language in action, details about the optimization and fine-tuning tool for the model, and information about the weights. A comparison is shown between different models, highlighting the distinction between ChatGPT, which is open source, and Alpaca, which lacks a dialogue fine-tuning process. On the other hand, Koala does have this process and has been evaluated with over 100 individuals. Further information is provided about the training dataset, including instructions on how to access many of these datasets. An evaluation analysis is presented, along with a discussion of the model's limitations. Perhaps the most interesting aspect of this model is the inclusion of the EasyLM tool, which allows for easy training and fine-tuning of large language models. The integration is seamless and instructions are provided on how to utilize it in various environments, including Conda. Although Koala is a recent model developed in the past few weeks, it appears to be highly promising due to its impressive performance. Furthermore, it offers the capability to adapt to specific use cases. Welcome to this module on LangChain, a tool that gives superpowers to ChatGPT. Throughout this module, we will learn how to empower ChatGPT with additional functionalities using the open-source LangChain toolkit. With LangChain, we can process large volumes of information such as extensive PDFs, link different language models, and provide these models access to external knowledge bases. Large language models like ChatGPT are generalists. This means that although they can generate information in a particular field, they may not be able to provide specific answers to certain questions or perform tasks that require deep knowledge or expertise in a specific domain. For example, we might want to use ChatGPT to answer questions about a specific field. While large language models could answer general questions about this field, they may not be able to provide more detailed or specific answers that require specialized knowledge or expertise. So, what can we do if we want to obtain more personalized or specific language models? The solution is to use LangChain. This open-source tool allows us to work with large language models and equip them with additional capabilities, such as the ability to learn from an external knowledge base. To overcome the limitations of large language models, LangChain offers a useful approach. It takes a corpus of text and processes it, dividing it into fragments or summaries. Then, these fragments are incorporated into a vector space, and similar fragments are searched for when a question is posed. For example, let's imagine we want to process a 90-page PDF. We know that ChatGPT has a limitation in terms of the amount of information it can process. Therefore, we could use LangChain to help ChatGPT learn from all that information. LangChain would take the text and divide it into vectors. Then, to answer a specific question about that PDF, it would search for the fragment containing the answer to the question based on similarity. This way, ChatGPT could respond in natural language using that knowledge. This method of pre-processing information and interacting with large language models is common and can be applied in other scenarios such as code search or semantic search. Additionally, LangChain provides an abstraction that simplifies the entire process of composing these text fragments. If we look at the LangChain repository, we will see that it has had impressive growth in the short time since its creation, receiving over 6,000 GitHub stars in just a few weeks. This demonstrates that it is a popular and useful library for users. In this task, we will discuss the different requirements of LangChain as well as the various models it provides access to. Regarding requirements, the only thing we need is an API key for our large language model. In recent months, we have been working with the LangChain model, and we have recently witnessed the emergence of a multitude of large language models where different developers or companies have developed their own models. Initially, the most well-known model was ChatGPT, but now various companies have also developed their own models, such as Llama, Bloom, or GPT. As users, we have the option to choose between proprietary large language models, which require an API key, usually paid, or open-source models, depending on the trade-off between performance and cost that we want to achieve. On one hand, we have proprietary language models, which are closed-source and owned by different companies, developed by experts. Generally, they are larger than open-source models and therefore offer better performance. However, it's important to note that their APIs come with a cost. Some examples of well-known proprietary models would be those from OpenAI, but there are also models from Kojira, AI21, OLAPS, or Anthropic. On the other hand, open-source models tend to be smaller and have fewer capabilities compared to proprietary models, but they are more cost-effective, and most of them are completely free. Some examples of open-source models would be Bloom, developed by VG Science, Llama, developed by Meta, Flanty 5, developed by Google, and GPTJ, developed by Aluther AI. As we can see, we have the option to choose from different types of large language models based on whether we need more performance, in which case proprietary models are preferable, or if we require lower costs, in which case we can turn to open-source models. It is recommended to explore the Hugging Face website, a platform where various open-source models are published, providing access to different models. As we already know, there is a wide variety of large language models available, and LangChain offers integrations for many of them. Additionally, it provides a simplified interface to connect with the different models. In LangChain, we differentiate 3 types of models based on their input and output types. First, we have the conventional large language models, such as ChatGPT, which take a text string as input, the user's prompt, and generate a text string as output. Next, we have chat models, which are similar to the previous ones, but instead of a single text string, they take a list of chat messages as input and return a chat message as output. In other words, the input for these chat models would be a conversation rather than a single input text. We have the embedding models available as well. These models take text as input and return a list of numerical values, known as embeddings. These embeddings are the numerical representation of the input text. These numerical representations help extract information from the text, which can then be used to calculate similarities between texts or generate summaries. Another example of their use is when they receive text as input, but unlike other models, embedding models do not provide a text output. Instead, they offer a numerical representation of the input text. As mentioned before, this representation can be used to assess similarity between different input texts. To get a better understanding of how these different types of models work, it is recommended to review the LangChain documentation, specifically the Models section, where you will find relevant information. In that documentation, there is a section called Getting Started that provides practical examples. We mentioned that there are essentially two types of models: conventional models and embedding models. Within conventional models, we have the standard large language models, LLMs, and chat models. How do they work with LangChain? First, it is necessary to import the corresponding libraries, just as you would normally do in Python with any other library you're using. You would use the OpenAI class for conventional models or the chat OpenAI class for chat models. The process is as simple as invoking the imported model and using the predict function, passing it the prompt. For example, if the instruction is for the chatbot to say hello, the chat response will be exactly that, hello. For the chat model, the procedure is similar. You use the chat model.predict function and pass it the input text. As you can see, the usage of these models is quite straightforward. Additionally, we have the option to add messages, as in this case, using the human message function. This function is very similar to the one described earlier, and by using it, we obtain the chatbot's response. Regarding the models, we mentioned that we have three types: conventional LLMs, chat models, and embeddings. You can access each of these sections in the Getting Started section to learn how each of them works. For example, let's consider the chat models, which are very similar to the previous ones. First, we import the function, which in this case is chat OpenAI, and then we directly pass the input text. In this example, we are passing different concatenated messages to ask it to translate a phrase. Later on, we pass the phrase "I love programming." We can proceed this way or chain different messages for the chat, which is done as follows. First, we introduce the system message, which is a kind of message to the system indicating what the chatbot should do. All of this is explained in detail in the documentation. As we mentioned, it allows us to concatenate different messages and then obtain the result. If you have any doubts about the different model types, simply refer to the Models section in the LangChain documentation. In this task, we will learn about the prompt functionalities in LangChain. To achieve good results with large language models, we know that using appropriate prompts is crucial. The process of generating these prompts is known as prompt engineering. As we have seen in previous tasks, this prompt engineering part and providing concise, relevant, and contextual instructions to the language model is essential. It makes a difference between getting average results with models like ChatGPT or achieving good results. Once we have designed a well-crafted prompt, it is common to want to use it as a template and reuse it multiple times. That's why LangChain offers prompt templates that help us construct prompts using multiple components. How do we use these prompt templates? As shown on the screen, the first step is to import the prompt template function from LangChain. Then, we construct the template variable, which has a fixed, invariant part and a variable part represented by arguments. In this case, the argument is product. This product argument will be modified based on the call we make. We generate the prompt using the prompt template function, passing the input variables, in this case, product, and the complete template. When we want to use the large language model with this template, we simply use the prompt.format function and indicate the input variable, in this case, product. We specify that it will be colorful socks. What are we doing with this? We are providing ChatGPT, for example, with the command "what is a good name for a company that makes," and instead of product, it will take the value we specify in the call, in this case, colorful socks. If we want to pass the product name as multicolor sneakers, we would put multicolor sneakers here. By doing this, we generate a standard template to obtain names for companies related to different products. If we want a colorful socks name, we put colorful socks. If we want sneakers, we would put sneakers here. This way, we can reuse the same prompt for different use cases. Additionally, if we observe this prompt, we haven't provided any context or examples to the large language model. As we have seen before, a prompt engineering technique is to send a series of examples, known as fused prompting, so that ChatGPT learns from those examples and identifies what is intended correctly. How do we include this prompt engineering technique through LangChain templates? Import the prompt template function and also the fused prompt template function. Next, we define the examples on which the model, such as ChatGPT, will learn. We indicate that for the input happy, the output should be sad, and for the input tall, the output should be short. In this way, we provide two examples. As we can already infer from the examples, what we are aiming for is to obtain the antonym of the input word. Next, we define the template, word that will take this variable and antonym that will take the next variable. In the template, we pass happy, which should result in sad. Then, we use the prompt template function to construct the template, passing the input variables that will take the meanings we want. That is, we will pass the desired input word, and it will use the example template. Then, we use the fused prompt template function, which utilizes the examples, the example prompt we defined here, and the prefix we pass. The instruction we give to ChatGPT would be, as the prompt, give me the antonym for each input. The suffix, which in this case would be the examples, would be word with input, and we had previously defined input as the first word, followed by the antonym. By doing this, the model learns, and finally, we pass the variable for which we want to obtain the antonym, which we do here. In this case, we will use the template that has a fused prompting program to obtain the antonym of big. This way, we can generate templates that are much more effective than if we don't use examples, as shown on the left. It is a bit more complex to generate, but it is much more effective in obtaining good results. In this task, we will learn about the chaining component in LangChain, which allows us to combine our large language model with other components. Chaining in LangChain refers to the process of combining large language models with other components to create a unified application. Some examples include combining large language models with request templates, sequencing multiple large language models, combining large language models with external data, and combining large language models with long-term memory. To achieve this, we can use the LLMChain function in LangChain, which is the function we see here. In this case, it is a simple chaining where we are only specifying the input variables to relate a prompt to those input variables. If we want to create a more complex chaining process, we can use the simple sequential chain function. In this case, we would be chaining multiple components, on one hand, the prompt we generated here, and on the other hand, an additional command where we want to get a short phrase for the company. We would be getting the result of the prompt we are using here, and also chaining the result of the second command. This second component is a bit more complex. We generate it using the prompt template function, and we need to pass dynamic input variables that will be modified based on our needs. Then, we have the template with a fixed part and the variable part with the input variable. After that, we use the LLMChain function to establish the relationship between these two prompts, and finally, we combine the first and second prompts using the simple sequential chain function. We pass chain 1, the chain 2 we just generated, and that's it. We can directly execute both commands related to a single call with the run command. We pass colorful shorts, which is the company name, and it will return the result of the chaining of both commands. Finally, if we execute this code, we will get the result of the first prompt, which is to get the company name, Happy Shocks & Co., and then the second prompt will automatically be launched, giving us a short phrase for that same company along with the new company name. So, the result will be step into colorful comfort followed by the proposed company name. The first part comes from the result of the first command, and the second part comes from the result of the second command chained with the first. This method will be useful, especially when we need to combine outputs. For example, if we want to ask ChatGPT for multiple things, and we want to perform one action based on the results of another, this would be the ideal scenario where we can use chaining. In this task, we will learn how to use LangChain indices to give ChatGPT access to external data. Large language models have the limitation of not having access to contextual information, such as specific documents or specific information. However, this limitation can be overcome by using LangChain. LangChain allows us to load external data using a document loader. It offers different loaders for different types of documents, such as PDF documents, emails, websites, or even YouTube videos. Once the data is loaded as documents, they can be indexed using a text embedding model in a vector database, such as Pinecone or Weaviate. In the next example, we will use FAISS, a vector database that does not require an API key. We will start by importing information from YouTube videos directly. To do this, we need to import the LangChain functions from document loaders, which will allow us to load information from YouTube videos using the YouTube loader function. We simply need to provide the URL of the video and use the .load function to load the information. Once we have loaded the information from the YouTube video, we convert it into a document and store it in the FAISS vector database. At this point, the document, which in this case is the video, is stored as an embedding in FAISS. Now we can use this information to ask specific questions about the YouTube video. To do this, we use the chain function, specifically the retrieval QA function, which allows us to ask questions. We define the query we want to ask related to the video we just loaded and launch this question to the model in QA format. The model will search through all the information it has acquired from the YouTube video and return a result to us. This is extremely useful when we want to enrich our natural language model with updated information or specific documents. We can obtain large language models specialized in a specific topic. For example, if we pass a medical document that talks about the brain, our model could acquire that specific knowledge, and we could ask it natural language questions for it to respond using the information it has learned from that brain article. This can be extrapolated to different use cases, as we have seen in this case with the YouTube video, or even trained with enterprise databases. In this task, we will learn how to enable large language models like ChatGPT to access other tools using the LangChain Agents module. While large language models are powerful, they have certain limitations such as lack of access to contextual and specific information, inability to perform precise calculations, and the risk of quickly becoming outdated. To overcome these limitations, they can be connected to other tools through LangChain agents. These agents can provide them with additional capabilities such as internet search, example, Google search, calculations, Python, Perl, or Wolfram Alpha, and access to specific knowledge sources, such as Wikipedia. Let's look at an example where we ask ChatGPT about Barack Obama's date of birth. Since this is a specific piece of information that can change and that ChatGPT may not know, we need to connect it to Wikipedia and a calculation tool to determine his current age. To achieve this, we first import the necessary functions from LangChain. We use the load tools function to load the Wikipedia and calculation agents. We initialize the agent with initializeAgent, passing in the tools and the language model we want to use. Once the agent is defined, we simply use the agent run function to execute the tools, allowing ChatGPT to access Wikipedia and perform mathematical calculations. When we ask for Barack Obama's date of birth and his age in 2022, ChatGPT can search for the date on Wikipedia and then use the calculation tool to determine his age. As a result, ChatGPT provides us with the requested information. Barack Obama was born in 1961 and was 61 years old in 2022. This agent functionality is extremely useful in providing additional capabilities to large language models like ChatGPT, enabling them to autonomously perform searches. Some models, such as AutoGPT, are developed using this agent functionality. Welcome to this module where we will learn how to train ChatGPT with a customized knowledge base. In other words, we will be able to train ChatGPT with the information we want, ranging from data in a database to information extracted from different PDF documents. In order to train ChatGPT, we need a customized document. When training ChatGPT with a database that exceeds the input token limit, we need to work with indices. So, how do indices work? Let's see a practical example using a PDF. In our case, we want to use a PDF that exceeds 20 pages and, therefore, greatly exceeds the allowed number of tokens. Once we have this PDF, the first thing we need to do is extract the text data from it using any library, essentially extracting the content of the PDF. After extracting the content from the PDF, we need to split it into different groups that do not exceed ChatGPT's token limit. Once we have these fragments, we place them into a customized document. These fragments will be converted into embeddings. These embeddings are essentially numerical vectors that represent the content of each fragment. In other words, each word will have a numerical representation, forming a kind of compressed fragment that language models can understand and utilize. Once we have the processed fragments in embedding format, the next step would be to generate a semantic index to create the vectorized database that holds the information of the embeddings. Once we have our vectorized database, the user can make a new query to ChatGPT, which in turn has access to this vectorized database containing the content we had in the PDF. The user will input a prompt-formatted question. This question will query the embeddings and perform a semantic search, retrieving the most significant fragments or results related to the user's question, based on similarity or context. Using the user's question, we will find the fragment that contains the answer in our vectorized database and generate a ranking of the best results. This ranking of results is then passed to the generative AI, the large language model, in this case, ChatGPT, so that it can generate a response using the knowledge from the embeddings. In other words, ChatGPT will have access to the useful knowledge from the PDF to generate a response for the user. This is, in broad terms, how indices work. Now let's see in detail how they are programmed in LangChain. As we have seen in previous tasks, in LangChain we can use a set of functions to give ChatGPT access to external data. These external data can be text contained in a PDF, as in the case we are about to develop, or it can also be audio from a YouTube video. In the first step, we always need a pre-processing or data extraction phase. In the case of using a YouTube video, we can use one of LangChain's document loaders modules, which allows working with YouTube videos to extract the text from the audio. Once we have done that and extracted the text, we need to process that text in some way to convert it into an embedding and then store those embeddings in a vectorized database. In this case, a vectorized database called FAISS would be used. Once we have the vectorized database, the user simply asks their question, and we access this vectorized database to extract the most significant embeddings. That information is then sent to ChatGPT, which returns a response. We use this function, then generate the question in this way, define the query, and once we have defined the question using the retrieval function type, we pass the question and obtain the result. Now that we have explained the theoretical process of training ChatGPT with knowledge from external databases, whether it's YouTube videos or information in a PDF, in the next task, we will continue with a practical lab. Welcome to this practical lab where we will learn how to train ChatGPT with information that we have stored or contained in a PDF document. To do this, we will use the LangChain index module. The first thing we need to do is access the WebCollab environment and upload the following notebook. Once we have uploaded it, we will need to install the libraries that we will require. Just as we did before, we have to import the functions that we are going to use. To read the PDF, we will use a Python library called pypdf and import the PDF reader function. Afterward, we will use a series of functions from LangChain. We will use embedding functions, functions to segment the text, and functions to vectorize the text and store it in a vector database, like FAISS, which we mentioned before. There are different types of databases we can use depending on our needs. We will also require prompt functions and access to a proprietary model which will be ChatGPT, obtained from OpenAI. As we are going to use ChatGPT, a basic requirement is access to its API key. We have accessed the OpenAI environment in the key section and generated a new one and added it. Once we have access to this model, we will see the result we get when we do not have access to the PDF information, and then we will see the result we obtain when we do have information from the PDF. The PDF we will use is this document that discusses GPT-4. We will do a test and ask ChatGPT who the authors are, who would be these ones we have here. To do this, we generate a simple prompt using the prompt template, pass it a dynamic variable which will be the question, define the OpenAI model, and with the exchange.ren function, we will ask the question. Who are the authors of the article? And it gives us this list of authors. If we quickly go to the article and go to the authors, we can see how it is making up the names of the authors. This would be an example of an incorrect response that ChatGPT returns to us, in which, since it does not have access to the article, it is inventing the authors. Anything we asked it about a specific article that it has not been trained with, it will not be able to answer, or it will give us a wrong answer, as is this case. How can we train ChatGPT with an external knowledge base obtained in a PDF? The first thing to do is read the PDF, as we had already mentioned. The PDF must be uploaded here. We would click here to upload files, and this would be the file. So now it will have access to the file through Drive, and with the PDF reader function it would already have reading access. It gives us a green check mark, which means it has been executed correctly. To execute the code, we can go to the execution environment to execute all the cells or execute them one by one. Once we have read the text, it has to be given a specific name, which is rootist, and what we would be doing here is iterating page by page in the pages obtained from the PDF. From the pages obtained from the PDF, the text is extracted and added to rootist. Each page is added as a sort of group. The content of each page would be this text grouped here. We can see that there is a lot of content. Here we could see the structure it has. Once we have done this, we can also access a specific sentence. With this, we would be accessing the first 100 characters, which would be the title of the article. We can check how it obtains it correctly. Then, we need to fragment the text into smaller fragments so that it does not exceed the token limit it accepts. For that, we would use the character text splitter function. We give it access of about 1,000 chunks and thus generate the different fragments with a maximum of 1,000 tokens. We can see that we get 8 fragments and we could access each of these fragments. The 0 would be the first fragment, 1 the second, and so on. Then, we have to create the embeddings. For that, we have to use the OpenAI embeddings function. Once we have generated them, we will access the embeddings database, in this case FAISS. With the friendText function, we pass it the set of segmented texts with a token limit that does not exceed ChatGPT's capacity. And we are also going to pass it the embeddings function. With this, our embeddings database would be generated. Next, we are going to import a series of functions from the chain. Specifically, the question answering function so that we can ask ChatGPT questions about the content of the embeddings. And therefore, the content of the PDF. We define the model using the loadQueryChain function. We obtain the OpenAI model, and once the type of model is defined, we can program the queries. The first question would be, who are the authors? We need to use the dog search function to search the database. We are going to use similarity search and pass it the question, the query. So in dogs, we would have programmed the similarity search in the FAISS database. Here we generate the FAISS database, and here we are doing this database which we have called dog search. And finally, to execute the command, we use the chain ren function to send the query to ChatGPT, which in turn what ChatGPT is going to do is obtain the embeddings, interpret the information from those embeddings, and with the generative guidance compose a response. What would it be doing here? It takes the embeddings as input, those embeddings that are most similar to the question, and launches the query. And here we have that it answers us that the authors are these ones. Let's see if it matches Uvanes, Anan, and Zach. Here we have it. We can check how it has been able to identify the names of the authors. Something curious is that many OCR interpreters or readers only get the first part of the authors without being able to interpret that the seconds are also author names. However, ChatGPT has been able to interpret that the authors were in 2 rows and has returned us the names of all. And now we can ask it as many questions as we want. We define another query: what is the cost of training GPT-4? GPT-4 is a version of GPT that has recently been released, and therefore ChatGPT has not been trained with the information of GPT-4. In fact, it does not know what GPT-4 is, and the answer to that question is here in the document. So we are going to ask this question, and it tells us $100. Now if we do a search in the article, we can see that indeed it is giving us the correct answer, that the total cost is $100. Another question we are going to ask is, what was the trained model? The model trained with LoRa gives us the information, how the hyperparameters were defined, and how it was done. We will also ask what was the size of the training dataset. And it gives us this size. We can contrast the answer it gives us with the article, and we can see how indeed it is giving us the correct answers. So we could ask it as many questions as we wanted. For example, how does it differ from other models? And with what it has learned from that article, it compares it with GPT-3 and gives us an answer. And finally, we are going to do a test to see if it works well, and that is we are going to ask, what is Google Bar? Which is another model that has recently been released whose information is not contained in this PDF, nor has ChatGPT been trained with that information. And then it answers us that it does not exist, which is correct. We can check how indeed ChatGPT would be accessing all the information contained in the PDF and would be giving answers based on that content. Welcome to this module on vector databases. Throughout this module, we will delve deeper into vector databases, which allow us to enhance large language models with additional knowledge. There are two main ways in which large language models can be used. One is through fine-tuning during training, and the other is through the model's inputs. In model training, also known as fine-tuning, we adjust the weights of the model. The more recent method involves model engineering, also known as the model phase. The other more recent approach involves prompt engineering, where we add information and context to the prompt, and this is done through the inputs. We pass knowledge directly to the model in the prompt and incorporate it as context in the model's responses. Fine-tuning is useful for specialized tasks, while providing context allows for more precision and enables the use of knowledge in the responses. However, OpenAI's GPT-3 model has a limitation in terms of the character length it accepts in the context, which is 4,000 tokens. This isn't very long considering the length of most documents. One solution would be to pass summaries of the documents or break them down into smaller chunks. Anthropic has developed a model called Cloud, which can handle up to 100,000 tokens per context, but this incurs a higher cost and also requires more processing time. Although increasing the context length helps the model acquire more information, new model architectures and solutions are needed to address context-related challenges more effectively. One effective way to pass knowledge to the model is through vector databases. Starting from a large corpus of knowledge, we would break it down into different fragments, transform these into embeddings, and then orderly store them through a semantic index in a vector database. This vector database allows us to perform a semantic search for the most relevant information fragment to answer the user's question. Thanks to this system, the model could utilize relevant knowledge in its responses without the need for a fine-tuning process or an increase in the token capacity that the model accepts in the input. This is why vector databases have gained significant relevance in recent months, with more advanced and efficient vector databases being developed. How have these vector databases been developed? Initially, we started with traditional databases, which were relational databases queried through SQL. They were designed for structured data and depended on fixed schemas. We then moved towards unstructured databases, the NoSQL databases, which offer greater flexibility in handling unstructured or semi-structured data. Finally, in the latest development phase, vector databases were developed. These vector databases provide an optimized solution for managing and querying high-dimensional vector data, i.e., data fragments transformed or derived from texts. These types of vectors are, in fact, what large language models use to work with texts. In this task, we will focus on explaining what vector databases are, as well as their characteristics. Vector databases, also known as similarity search databases or nearest neighbor search databases, are specialized databases designed for efficient storage and querying of vectors. They are particularly beneficial for data development applications. Unlike traditional databases, which are optimized for operations such as index search or structured data query, vector databases focus on the search and retrieval of information based on vector similarity. These databases offer advanced capabilities for working with vector data. They enable operations such as finding elements most similar to a given vector, calculating the distance between vectors, searching for elements that meet specific similarity criteria, or performing range searches. These functionalities are especially useful in applications that require efficient information retrieval based on similar features or attributes. The popularity of vector databases has surged due to the growth of applications using machine learning algorithms and vector-based word representation models, known as large language models. These models generate vector representations of data, facilitating similarity comparisons and searches among them. Vector databases provide an optimized environment for storing and querying these vectors. It's also noteworthy that vectors are not only derived from processed text, but any unstructured data, such as images, audios, or videos, can be transformed into vectors through various transformers. Subsequently, these vector databases can be used to search for instance, images similar to each other or audios similar to each other. Regarding the features of vector databases, several points stand out. First, they support vector similarity search, which identifies vectors closest to a specific query vector. According to the similarity metric, this process will yield a list of the most similar vectors. Vector similarity search is beneficial for applications such as image search, natural language processing, recommendation systems, or even anomaly detection. Moreover, vector databases use vector compression techniques to reduce storage space and improve query performance. Another key feature of these databases is their ability to perform an exact or approximate nearest neighbor search, depending on the desired balance between accuracy and speed. Exact nearest neighbor search offers perfect result or similarity, but it can be slow, especially with large data sets. Conversely, approximate nearest neighbor search utilizes a series of algorithms to accelerate the search, potentially at the expense of result accuracy. These databases also support different types of similarity metrics, such as L2 distance or cosine distance. Various similarity metrics can be adapted to different use cases and types of data. Lastly, the distinguishing feature of vector databases is their capacity to handle a range of data sources, such as text, images, audio, or video. These data sources can be transformed into vector embeddings using machine learning models, such as word embeddings, sentence embeddings, or even image embeddings. Now that we have a better understanding of this type of database, our next task will delve into the different vector databases currently available. In this task, we will discuss the most popular vector databases currently in use and learn about the differences between vector databases, libraries for generating vectors, and plugins. We will begin with a list of the most popular vector databases currently in use, which are detailed in the description table. One of the best known is FAISS, developed by Meta. FAISS is a library for efficient similarity search and clustering of dense vectors. It can handle vector sets of any size and provides support for parameter evaluation and tuning. Next, we have Milbus, an open-source vector database capable of managing large vector datasets. Milbus supports multiple search indices and has built-in filtering capabilities. Another database is Quadrant, a vector similarity search engine and vector database that provides a production service complete with an API for utilization. Elasticsearch, another widely recognized platform, is a distributed search and analytics engine that also supports vector fields. It provides support for efficiently indexing and searching vectors. Following Elasticsearch, we have WebAvid, which is an open-source platform that allows for the storage of vector objects and embeddings. We also have the Vespa search engine, a vector database that supports vector search, lexical search, and structured data search. Then we have pgvector, an open-source extension for PostgreSQL that enables storage and querying of vectors within the PostgreSQL database. Finally, we have Pinecone, a vector database designed for machine learning applications based on the FAISS library. It is fast, scalable, and compatible with various machine learning algorithms. We will now discuss different vector storage systems, as there are not only vector databases but also vector libraries and plugins. We'll start by discussing vector libraries. These libraries create indices that enhance search efficiencies. If you don't want to integrate with a new database, you can use a vector library that creates these indices for you. A vector index typically consists of three components: preprocessing, where you can normalize or reduce the dimensions of the vectors, the main step, which involves an indexing algorithm such as FAISS, and post-processing, where you can quantize or hash the vectors to optimize search speed. A library like FAISS is sufficient for small, static data. However, vector libraries lack properties that databases have, such as cross-support or disk storage. The index must be completely rebuilt from scratch each time there are changes in the data. The choice between a vector database and a library depends on the frequency of changes in the data and whether you need all the properties of a complete database. On the other hand, there are also databases or search systems that offer vector search plugins like Elasticsearch and PageVector. These plugins usually have fewer features and options for approximate nearest neighbor calculations. Finally, when it comes to vector databases, the decision is based on three key aspects: the amount of data we have, usually in the millions or billions of records for utilizing vector databases, the speed required for queries, and whether all properties of a full database are necessary. If your data is static and you don't frequently update it, you could start by using the vector library. However, if your data changes rapidly, pre-calculating the embeddings and storing them in vector databases for on-demand queries might be more efficient, thus avoiding the real-time computation of vectors and indices. Adding a vector database does involve additional costs and requires learning and integrating an additional system. Therefore, based on the volume of data and the requirements, we may choose a vector database, libraries, or in some cases, plugins. In this task, we will discuss various vector search strategies and the metrics used to measure the similarity between vectors. In vector search, there are two primary strategies to identify similar vectors: exact search and approximate search. As its name suggests, exact search employs a brute force method to find the nearest neighbors, leaving little to no margin for error. This approach aligns with what the k-nearest neighbor method typically does, symbolizing exact search. Conversely, with approximate nearest neighbor (ANN) search, you find less accurate nearest neighbors, but you gain in speed. In other words, you trade accuracy for speed. Within this search strategy, we find several indexing algorithms. We refer to them as indexing algorithms because their output is a data structure called a vector index. This vector index assists us in maintaining all the necessary information for an efficient vector search. Among these algorithms, tree-based methods, like Annoy by Spotify, stand out, alongside proximity graphs, clustering systems, LSH systems, and product quantization systems spearheaded by FAISS, developed by Facebook. Hashing and vector compression also play significant roles, with the SCAN algorithm developed by Google leading in vector compression. In summary, we have two distinct search strategies: nearest neighbor search and approximate search. The former is more accurate, and the latter is faster, albeit less accurate. Next, let's discuss the metrics we will employ to determine whether two vectors are similar. We achieve this through distance metrics or similarity metrics. With distance metrics, we commonly measure the L1 distance, known as Manhattan, or the L2 distance, known as Euclidean. The Euclidean distance is usually the preferred choice and is most widely used. A larger distance metric indicates that the vectors will be more dissimilar; in other words, there will be a greater distance between the vectors, and they will therefore be less alike. Alternatively, we can also measure the similarity between vectors using the cosine similarity measure. A higher similarity metric indicates more similar vectors. Thus, we can use either of these two metrics to determine the similarity between vectors and understand the degree to which they resemble each other. Welcome to this multi-stage reasoning module. Throughout this module, we will learn how to chain tasks using the chain function of the LangChain tool. Before we start explaining the reasoning module, let's reflect on the limitations that large language models have. While these models excel at traditional natural language processing tasks, such as summarizing text, determining class, or performing a translation, the limitations of large language models are significant. For translation, most workflows require more than a simple input and output. Therefore, we must find ways to combine large language models with other pieces of code efficiently and without disrupting the entire system. As we just mentioned, these large language models are great at individual tasks, but they are not as good when it comes to performing batch tasks or highly complex tasks. Batch tasks would include, for example, translating multiple articles simultaneously. And when we refer to complex tasks, we mean tasks that require more than one step to obtain a result. Let's consider a case where we want to analyze articles from a newspaper and derive the general sentiment of the newspaper. To do this, we would need, on one hand, to summarize the articles, emphasizing the sentiment, and then pass these summaries to a model that can provide a comprehensive sentiment of the newspaper. Accomplishing all this is not an easy task, and it can't be done all at once. If we believe that we could tackle this with a single large language model, we are mistaken, as it would be too challenging for it to handle everything at once, and moreover, it likely wouldn't do it well. A better strategy could be to take one article at a time, pass it through a specific large language model to generate summaries, and then, from the output of that summary, feed it into another specific large language model for sentiment analysis. This modular approach would enable us to build reusable and flexible tools that could address a task in different stages for different elements, in this case, for different articles. To implement this, we will turn to prompt engineering and workflows. We can create prompts with input variables to generate workflows that allow us to carry out the same task as many times as we have inputs. In the previous case, we would need to generate a workflow that summarizes all the articles in the newspaper, and that's what we're going to start programming. The first thing we need is a template that takes an input variable, which would be the article. Here we have this prompt where we instruct the large language model to summarize the following article, paying special attention to the emotional aspect, and we pass the article as a variable. This allows us to modify the article we provide in each execution, thus iterating through different articles. Then, we ask it to produce the output, which would be the summary. Next, we will use the prompt template function to generate the prompt. We pass the summary prompt template that we just mentioned as the template, and the input variable would be the article. What is the next step? It would be to iterate through all the articles to obtain the summaries, which is what we're doing here with a for loop. We're going to program a for loop that goes article by article within the list of articles and uses the summary prompt function we just generated. In this for loop, we will pass the next input article, and it will compose the prompt in each iteration, modifying this article. Once it has created the prompt, it passes it to the large language model to give us the summary. This constitutes the first part of our process. In the next task, we will explain how to program the second part, which was to use another large language model to obtain sentiment from the different summaries. In this task, we will continue with the previous exercise in which we will chain two large language models. We had previously programmed one to summarize the articles, and now we will program another to analyze the sentiment of these articles. Initially, we had created a workflow that iterated through all the articles to derive the sentiment from each one. Now, we will connect the result of this first workflow with the input of the next language model to provide the sentiment of the article, which is the second part of this process. To accomplish this, we will use the following code, which accepts as input the summary from the previous language model and returns the sentiment. For this, we need both of the already programmed large language models, which we can employ through the summarize and sentiment functions, and we will need to devise a new template. For this new template, we will prompt the model to evaluate the sentiment of the given summary. It will take a variable as input, which will be the summary. This variable will change according to the phase or the summary we input, and as a result, it will yield the sentiment. Hence, we will again utilize the prompt template function and pass this new template that we just created, which will take a variable as input, the summary. This will be located within the for loop, so as the loop executes for a specific article and obtains the summary, this summary is sent to this new prompt. Consequently, the second model, the sentiment model, returns the sentiment of that article. In this manner, we would have programmed a rather complex workflow. If we had asked the model to generate a summary for all the articles at once and then obtain the global sentiment, it probably would not have worked effectively. Conversely, with this iterative approach, the language model needs to perform a minor task in each iteration, thereby ensuring successful completion. In this task, we will continue to delve into the chaining of prompts thanks to the chain module of the LangChain tool. Chains are a feature of LangChain that allow us to combine multiple components to create a unique and coherent application. Although there are various ways we can combine different components, the most common use case involves combining the output of one prompt, or an instruction in ChatGPT, with the input of another, so that ChatGPT uses the output to return another prompt to us. This is akin to allowing ChatGPT to perform tasks sequentially and learn from the results of each task. We can accomplish all of this thanks to the chain module of LangChain. In the next task, we will develop this use case by combining a total of 3 prompts or instructions in ChatGPT. We will send an instruction to ChatGPT, ChatGPT will provide a result, and this result from the first command will be combined with the result of the second command, and so on. In this case, we are going to use the LangChain model. The first thing we need is a code execution environment. In this case, we will use Python, although other programming languages could also be used. To simplify things, we are going to use the WelcaLab environment. To access WelcaLab, you simply need a Gmail account. After searching for WelcaLab in the Google search bar, the environment will appear. The great thing about WelcaLab is that it already has Python installed, so there's no need to worry about installing anything on our local environment. The main page provides access to the file section, where we can upload a notebook. This notebook is essentially a repository that contains the code we want to run. The next step is to drag the chain and prompt notebook with chain and LangChain to the file selection area, after which the notebook will automatically open. The first step to executing any function is installing the libraries for that function. In this case, we are going to use LangChain as expected, and also the YamaIndex library, which will allow us to work with indices. Once we have installed them with the pip install command with an exclamation mark, they will be installed in the WelcaLab environment and this tick will appear, which indicates that they have been correctly installed. To execute the code, we can click on Execute Cell. Alternatively, to execute all cells, we can go to the runtime environment and click Execute All. Both options are valid. For example, if we want to execute this cell, we would execute it. The next step is to import a series of functions that we will need. We are going to import a large language model from OpenAI specifically for ChatGPT. Additionally, we are going to import some extra functions from the chain module, such as LLM chain and simple sequential chain. We will also use the prompt template to generate a query template. As we need more functions, we can use the import command followed by the function name to import them. A fundamental requirement for LangChain, as we had mentioned, is that proprietary models require access to their APIs. These are paid APIs. In this case, we are going to use the OpenAI model, so we have to go to the OpenAI environment and get the keys. To do so, just access this URL. You do need to enter a payment method. And once we have entered a payment method, to create a new secret, just add a name. We click on Create Secret Key and copy it. And that's it. It would appear here. To delete it, just come here and delete it. Now that we have the code, we are going to replace it and execute this cell. With this, we would be giving WebCollab access to this proprietary model of OpenAI. The next thing we are going to do is generate a simple prompt about a somewhat complex question. Specifically, we want to ask ChatGPT what type of mammal lays the largest eggs. Creating a simple prompt from Python code is very straightforward. We need to use the function we have already seen, prompt template. This function takes two arguments, input variables, which are variables that change depending on user needs, and the template, which is the basic question template. The template is simply an empty frame that holds the question variable. So, depending on the question we want to ask, we will ask one question or another. In input variables, we provide the single input variable, which is the question, and in the template, we provide the basic question template. To use this, once we have defined the prompt template, we can use the .format command to generate the question. We pass it the input variable, which is the question we had defined, and tell it that the question is equal to what type of mammal lays the largest eggs. This is the question that would be sent to ChatGPT. If instead of this question we were interested in asking, what is the weather like now? We wouldn't need to modify anything except the question. We could use this template for as many use cases as we want. This question is what is sent to ChatGPT, and now we will ask the question. To do this, we will define the model we are going to use. As we had mentioned, we are going to use the OpenAI model. We can also set its configuration. This would be the default setting, but it modifies how the OpenAI model behaves slightly. Once we have defined the model, which we have named LLM, we use the LLMChain function to call this model and send the prompt template we had defined earlier. Now we simply use the chain.run command, which is the chain we have generated in a single step. We call that chain with the run command and pass it the input argument that was the variable question we had put here, which in this case is what type of mammal lays the largest eggs. Then it will execute, send the query to ChatGPT, and we will receive the answer. And what does ChatGPT answer us? That there are no mammals that lay eggs, only reptiles, amphibians, and birds lay eggs. As we know, this statement is not correct since there is a type of mammal, the platypus, that does lay eggs, so this statement is not correct. This would be a case in which by asking a complex question in a single attempt the result we get is incorrect. In the next task, we are going to try to get better results by concatenating different subtasks, in this case different questions, and teaching ChatGPT with this to give us a final answer to the same question. In this task, we will continue with the hands-on lab to generate a series of chained prompts to get the answer to the question of which type of mammal lays the largest eggs. In the previous task, we had seen that with a simple prompt, posing the question to ChatGPT provided an answer to the question of which mammal lays the largest eggs. However, the answer ChatGPT gave was incorrect, as it stated that only reptiles, amphibians, and birds lay eggs. So we are going to try chaining prompts to get better results. The first thing we need to do is define the main question, which would be the same as we defined earlier. Once defined with the name question, we will begin to generate the chaining of the different queries. So we are going to generate 3 queries, 1, 2, and 3. Then, with the simple sequential chain function, we will chain them together. The first thing we need to do here is program the OpenAI model if we have not previously done so. For this, we use the OpenAI function, generate the template, which in this case is made up solely of a changing variable, which is the question variable, and use the prompt template function to generate this template. It takes the input variables, which would be just a single question variable, and then takes the template. Once we have this, we will use the LLMChain command to chain the query. So we use LLMChain, pass it the model we want to use, which is the one we just defined above, and then also pass it the prompt template. With this, we have the first entry, the main question, and now we will generate different sub-questions. For the next one, we will indicate that there is a statement and then we add a second variable, the statement variable, and also a piece of invariant text that indicates to make a list of points, known in English as a valid point list, of the assumptions it made when producing the previous statement. That is, with this we indicate to ChatGPT to list the assumptions it made to get the answer to the question which mammal lays the largest eggs. The goal of having this list is to then pass each of the points from that list individually to ChatGPT and tell it whether that assumption is true or false. If it discovers that any of the assumptions are false, it will know that the answer it was giving is also false. So we generate this second query for ChatGPT, we use the prompt template function again. This template takes 2 arguments, it has the input variable equal to statement, which is what goes here, and as a template it uses this template. We use them chain again to chain the prompt and we indicate which model to use, which is the same as before, and which prompt template. Now in a third step, we will pass it a list of statements, which would be the assumptions it generated here, and we will indicate that for each statement, determine whether it is true or false. If it is false, explain why. And it takes a variable which is assertion, which is what is generated here. So we use the prompt template again, we pass this variable and the template, and with the LangChain function, we chain it again. Now we are going to add a final step in which we are going to indicate to ChatGPT that in light of the previous information, how would it respond in this case to the original question, which is the Q that we had defined before. We use the prompt template function again, it takes this second template, an input variable that would be fact, which it will get from the previous step, and we indicate the template again. We chain this step again and we would have 4 calls to ChatGPT using the same model and the prompt template that we just defined. Once we have the 4 queries that we want to send to ChatGPT, they need to be chained. We are going to generate a sequential process so that the results of the first prompt are the input to the second prompt and the results of the second prompt are the input to the third prompt and so on until finished. We use the simple sequential chain function, we indicate which chains it has to use, which prompts, so it would have to use the question chain, which is the first one we defined, the assumption chain, the fact checker chain, and the answer chain, and they would be executed sequentially. How do we execute it? Well, simply with the run function. Once it is defined, with run we indicate the input question, the Q, which was the initial question we wanted to answer, and with this, it is executed. So the question we want to answer is this one, what kind of mammal lays the largest eggs? And what does ChatGPT do? Let's see, let's run it. Here we can see how the process starts. This is the first sentence of the answer chain, and here it starts with the first part, which is to list the assumptions it has based on to get this answer, and it tells us that mammals include the platypus. And why the platypus? Because it already answers us that platypuses are the type of mammals that lay the largest eggs. So, To arrive at this conclusion, the assumptions are that mammals include the platypus, platypuses are capable of laying eggs, that platypus eggs are large compared to other animals. These would be the assumptions, and then we would move to step 2, which is to say whether the assumption is true or false. So, in step 2 it is reviewing the assumptions. So, mammals include the platypus, true, platypuses are capable of laying eggs, true, platypus eggs are large compared to other animals, false, but although this is false, the rest are true. It's just that the statement that platypus eggs are large is not large, as far as we can see they are small. So, as a result, it gives us this. Once it has shown the assumptions it bases on, it has contrasted them and has learned from that information, which would be in the last step that we indicated to it to use that information to respond. Then based on these assumptions it responds to us that platypuses are not the type of mammal that lays the largest eggs, but it tells us that platypuses do lay eggs. This would be the result that the prompt chain gives us, and finally the final result. As we can see, while it is true that it tells us that platypus eggs are not the largest, it does tell us that mammals lay eggs. If we go back to the previous step, it had told us directly that mammals do not lay eggs, that only reptiles lay eggs. Here it has already been able to identify a type of mammal, which is the platypus, that lays eggs. Now, if we reissue the query, by clicking directly on the cell, we will see how the results vary slightly and it will show us another result. We can see how the assertions are slightly different. It talks to us about monotremes, which are a group of mammals, and they are the only known mammals that lay real eggs. Here it says there are 2 types of monotremes, the platypus and the echidna, but that platypus eggs are larger than those of the echidna, so the mammal that lays the largest eggs is the platypus. Here it has given us a much more accurate and precise answer. Welcome to this module of the LangChain Agents course, designed to integrate new capabilities into ChatGPT. Throughout this module, we'll learn how to use the LangChain Agents module to grant ChatGPT new abilities and integration with supplementary tools, such as Wikipedia or internet search engines. As we previously stated, large language models have significant constraints, particularly concerning the lack of contextual information. Typically, these models are trained with information predating 2021, although ChatGPT-4 has more recent data. This means they're not models that can be applied in specific contexts requiring updated or highly specific information on a particular subject. To overcome these limitations, it is essential to furnish ChatGPT with additional functionalities. How do we accomplish this? By granting it access to complementary tools, such as internet browsing, calculation methods, or even the capacity to make independent internet queries. Next, we'll examine a code sample that employs the Agents module to incorporate Wikipedia access functionality into ChatGPT. Firstly, we must import a range of functions, including those from load tools for loading tools and agent type for integrating agents. Then, using the load tools function, we indicate which tools we want to use, in this case, Wikipedia and a math tool, as well as the model we intend to use. Afterward, we initialize the agents with the initializeAgent function, indicating the list of tools to be used, and we also configure the agent to return results with 0 short prompting. To execute the agent, we simply use the agent run command, launch the query, and automatically grant ChatGPT the ability to seek information on Wikipedia and perform mathematical operations. Thanks to this, ChatGPT can answer questions like Barack Obama's birth date. In this scenario, ChatGPT would search Wikipedia and then use the calculator to determine the time elapsed from his birth until the present day, providing us with an answer. Integrating with agents opens up a world of possibilities for ChatGPT, allowing it to utilize additional functionalities to compensate for its limitations. This agents component is particularly helpful when we want to program a large language model, a chatbot capable of accessing various tools, or even when we aim to program autonomous models like AutoGPT, capable of conducting internet searches to acquire lacking information. Welcome to the second part of the practical lab where we will learn how to integrate different agents into ChatGPT. In the previous task, we had already used and obtained different agents, one for Wikipedia, another for Google Search, and another for performing mathematical functions using Python. Throughout this task, we will unify all these agents and integrate them into a single ChatGPT model. To achieve this unified integration, we will make use of the tool function. The first thing we will do is import the ChatGPT model from OpenAI, which we will call LLM. Once the large language model is defined, we can start using the tool function to unify the agents. Let's start with the OpenAI function. We need to use the tool function and pass several variables, the name we want to give to the agent, which we recommend using the agent's own name, the function which is the Python_red function that we have tested here with the ren function for execution, and an optional description explaining what this agent does. We will do the same for Wikipedia. We use the tool function, give it a name, pass the function which would be wikipedia.run, which is the same as what we have previously tested here and confirmed that it works, and provide a description. Finally, we program DuckDuckGo using the tool function. We give it a name, a function which is search.run, and a description. Next, to unify them, we had already added the first one to tool and named it tools. So, we need to append the Wikipedia and DuckDuckGo agents to this tools. We will use tools.append to add DuckDuckGo first and then Wikipedia. This way, all three agents will be integrated within tools. Next, we will program ChatGPT to be able to use these agents. To do this, we need to use the initializeAgent function. We pass the name of the agent, the tools it will use, the model it will use, which in this case is ChatGPT, a proprietary model. Then, there are optional parameters, as well as the number of iterations we will allow. If we print this newly programmed agent, the zero-shot agent, and access the template, it will provide information on how this model is developed. It will indicate that it integrates OpenAI's ChatGPT and the agents, which is what we can see here. It indicates that it has access to the different Python agents, rep, do, go, and Wikipedia, the template format it uses, and the input variables it takes. Now, all that's left is to test it. We will use the Python rel function, and for that, we use zeroshot.run, which calls the model that is integrated with the agents, and with the run function, we execute it. Then, we pass the input variable. In this case, we will pass a mathematical operation that will trigger the execution of Python rel. We will see that it enters the agent and needs to perform a calculation. It uses Python rel to multiply 17 by 6, and here we would get the result, which will also be displayed. If we ask it to tell us about Singapore, we use the run command again on zeroshot.agent and tell it to provide more information about Singapore. In this case, instead of using the Python rel agent, it will use the Wikipedia agent. It will search Wikipedia for information about Singapore, retrieve information about Singapore, and give us a result with related information about Singapore. Finally, we will use the agent for Google searches. Again, we use the zeroshot.agent.run function and ask it to tell us the current price of Bitcoin. It will initiate a search on Google through DuckDuckGo, retrieve the current price of Bitcoin, and return it to us. Lastly, we can even ask it to perform complex functions. For that, we will use the Python rel library or agent. We will ask it to write a function that validates if 11 is an odd number and test it. This library is not only capable of executing mathematical functions but is also capable of developing and testing code, as we can see here. It will develop the requested function, test it, and finally provide us with a response. As we have just seen, integrating agents into ChatGPT to enable it to perform Google searches, access Wikipedia, or even perform complex mathematical functions is made easy by using LangChain's agent module. Thanks to LangChain, we can equip ChatGPT with numerous capabilities and develop a highly powerful language model with a wide range of skills and abilities.